Okay, thank you. Put it here maybe. Yeah. Okay, good morning everybody. So we are going to have two wonderful invited talks to begin with. And the first talk will be given by Manoj Prabhakaran. So Manoj is the Vijay and Sita Vasi Chair Professor in the Department of Computer Science and Engineering at IIT Bombay. His research interests span theoretical cryptography, information security, and various topics in theoretical computer science and information theory. Prior to joining IIT Bombay, he was an associate professor of computer science at IISc. And amongst the many achievements he has in his illustrious career, some of them are, for instance, he was a BTech in computer science at the same institute, IIT Bombay, and he was the institute gold medalist. He received an IBM PhD fellowship and an NSF career award, a Beckman faculty fellowship, a Ramanujan fellowship. He is an associate editor of the Journal of Cryptology, a member of steering committees of Theory of Cryptography Conference and the Information Theoretic Cryptography Conference, and a member of ACM India Cybersecurity Task Force. At IIT Bombay, he heads the IITB Trust Lab. And of course, I mean, he is one of the stalwarts of cryptography and in particular MPC. Particularly, I have enjoyed his works on the topic of compilers, and I guess the whole community is really indebted to him for his wonderful work in that area. And it's my honor to introduce him in this forum. So over to you, Manoj. Thank you for accepting the invitation.
This is on? Okay. Thanks, Arpita, for the generous introduction, and also for inviting me here. And also thanks to all the organizers, and also thanks to all of you for coming early in the morning for this talk. So I'm going to talk about scales model. This is joint work with Anshiya Acharya, who is now at Aarhus, Karmit, who's here, Vlad Koleshnikov at Georgia, and Vlad Koleshnikov at Georgia Tech. Slides are mostly due to Ansuya, but I've changed a few things, so if you find anything wrong, that might be me. Okay, so we're talking about MPC, so I don't need to tell you what MPC is here. But the kind of flavor of MPC we are interested in, I would call it MPC as a service, but more as a crowdsourced service. Okay. And we are also interested in very large-scale computation. That's where some of these concerns come up, some of the benefits show. Okay, so you have a large crowd of servers who could hopefully help you with MPC, but of course many of them are corrupt. And you have a bunch of clients, again some of whom would be corrupt, who have some data with them and who would like to compute. So maybe they would like to compute some statistics of their inputs, or maybe a machine learning model. That's the right example nowadays. So they have their inputs, they would like to give it to this crowd, who would then talk to each other and hopefully get the right answers in a secure way. Right? But of course, this crowd is large. If you want all of them to help you, that's going to be very inefficient. So typically, you'd like to have a small subset of these people show up, do the work for you. This kind of brings up a new concern, which is that an adversary, if they could see who this committee is, okay, that's a committee kind of talking to each other and getting the work done. But if the adversary could see who this committee is, it's a small committee in this large crowd, maybe they could corrupt all of them. Okay, and then none of the guarantees of security would hold, right? So that's kind of, the setting where we'd like the adversary not to do this. So we'd like to keep this committee hidden from the adversary and that's one of the considerations. And for that, you'd like the committee, of course, once they speak, everybody sees who they are, so you'd like them to just speak once and not speak again. So about 5 years back, when blockchain was the hottest topic around, I guess before AI became that, there are a lot of works on blockchain-inspired settings, and I just cited a couple of them here. Can a public blockchain keep a secret? Benumuda et al. Another one quite influential, Yoso. So Sophia is here, and Gendry, Halevi, Kravchuk, Marguerite Nielsen, Rabin, and Jacobo. So these papers introduce this question of, can we do MPC using a large number of parties who all just speak once so that the adversary doesn't have a chance to go and corrupt them, okay? And our works kind of fit into this mold. So there are two papers that I'm kind of merging and going to talk about today. Okay, so I'll first spend some time describing the model and then briefly sketch solutions in these two papers. One is a semi-honest version, and the second one is the security against active corruption. Okay, so let me start with the model. Okay, so scales stands for, it's not just that we want it to mean that it's a computation that scales. It actually expands to something, small clients and larger ephemeral servers, okay? Or maybe linear-sized ephemeral servers. Okay, so let me explain what these things are. So yeah, the clients and the servers. So first thing is small clients. What do I mean by small clients? These are the parties who have the inputs, who care about the data. And there may be a lot of them, many of them. But each one is a small client. They don't care about the entire universe of all the inputs. They don't even want to spend as much time as it takes to compute the function in the clear, because of, it's a large-scale computation. That's our motivation. Okay, so what we'd like to do is to keep the complexity of each client proportional to its own input. It shouldn't depend not even on the total input size, let alone the total function size. Yeah, so it should be independent of the number of other clients. It can depend on things like the security parameter, but not the number of other clients. And any subset of these clients could be corrupt. Okay? And true to the blockchain motivation, all communication is going to be through a public bulletin board. Okay, so that's how the clients interact with the rest of the world. And they are not going to read everything everyone else posts, right? They just post their stuff and hopefully finally the answer. The other set of parties in this mix are the ephemeral servers. So these are the parties that come from that large crowd we saw in the beginning. So they come in one by one. We don't quite care how they're chosen. They could be chosen using some lottery. They could be self-selected. And typically, you would want them to be selected in an unpredictable fashion, okay, so that the adversary doesn't have time to, doesn't know who is going to come in until they come in and speak. Okay? What does it mean to speak? They do some computation locally. Nobody knows at this point that they're part of the computation. They can create a message they want to post on the bulletin board, erase their entire state, and just post this, accept this message, which they post on the bulletin board, right? And then they vanish, as in they have erased their state. And after one server goes, the next one comes, and each one does the same thing. They look at the bulletin board, so they can locally, read everything, do computation, then just come out, post what they want to post, and vanish. And at the end of all of this, yeah, so as I was saying, the servers can be dynamically elected, or self-selected, some lottery mechanism. And they're coming from the crowd, so we'd like to have minimal requirements on their honesty. So what we would typically like to work with is that all but one is corrupt, okay? So are corrupt. So only one is honest. At least one has to be honest, otherwise you cannot hope for any security if all of the servers who participate are corrupt. So this is the most minimal requirement you could try to make. No honest majority in particular. Okay, yeah. And it's not going to be enough often just to do this once. We'll have a couple of such phases, 2 or 3 in our solutions. In the model, we say a constant number of such phases. So in each phase, the client can come back and speak. Okay, so the clients are there, they are not ephemeral. And this one difference with a model like IISc model, where everybody speaks once, we get, one of the reasons we get some of the efficiencies we get is that the clients can come back and speak at each of these 2 or 3 phases. And so it's the same clients who come back. The servers are fresh servers. Of course, they could be some of the same parties, but in every phase, we would like one honest party. Okay? And at the end, the result will be publicly available. Of course, if some client wanted a private output, it could be masked by some one-time pad. That's also part of the client's input. But in the model, we say the output is publicly available. Okay, so to summarize, so that's essentially the entire model, or the important things about the model. So we think it's an attractive model for this MPC as a crowdsourced service. So as I said, small clients, ephemeral crowd workers, and they can join the protocol at any point dynamically. Another thing about being IISc or being ephemeral is that in this kind of large setting, you cannot really rely on them to come back. And we are not going to wait for them to come back and do anything, right? If we relied on these crowd workers to do several things, then there is a unreliability or efficiency issue that many of them would drop off, will not come back for finishing the computation. With ephemeral servers, you don't have that issue. All the communication is over a bulletin board, and that gets you some of these interesting things that blockchains give you, right? You can reward people. Cheaters can be identified publicly. They can have a reputation. They can get penalized. So that's one of the good things about this model. No secret committees or target anonymous channels. These are some of the tools that show up in some of the other works in this line. And since we have a slightly different model with clients showing up again and again a couple of times, we've managed to avoid any sort of committees. As I already mentioned, no honest majority. And the number of rounds is basically the number of phases times how many servers show up in each phase. We just need enough servers to show up so that we can, with high probability, have at least one honest party, honest server, right? And you could think of that as a constant, at least it's independent of the function's complexity. Okay, so some 20 or 30 or whatever number of servers show up in a phase, and we have 2 or 3 of these phases. So hopefully it's a reasonably realistic model. I'll talk about at the end, some of the challenges in making it really practical. Well, one challenge is that we are in a CRS model. It's not a big problem. A lot of the blockchain solutions are in a CRS. They have a CRS setup, and we also our solutions would also rely on a CRS, common random string, common reference string. Okay, so hopefully any questions on the model itself? Okay, yeah. A server can appear twice. We don't care. Okay, it's just that we don't need a server to maintain state between. Corrupt servers can do whatever they want. They can maintain all the state across all the phases. Okay, so I'll start with the semi-honest version. Okay, and our solution, again, this is our solution. completely reasonable that you could have a completely different version, a different solution. And I'll be happy to see alternate approaches. But our approach uses gobble circuits. And that kind of goes along with being non-interactive.
Manoj, I have a question on the model.
Yeah.
So does the clients collude with the servers?
Clients are allowed to collude with the servers. So any subset of the clients could be corrupt, and they'll be colluding with the corrupt servers.
Any number of servers
Yeah.
in a particular committee?
Yeah.
Both are malicious, right?
So right now I'm talking about semi-honest, but I'll talk about malicious. Yeah, we have both versions. So here, so just to remind you, gobble circuits, there's a gobbler who takes a circuit and gobbles it to get a gobble circuit, and also produces some labels for the inputs, right? The input, so here there are n inputs. So for each input, there is a pair of labels. And later, when you want to evaluate the circuit on some input x, the first thing you'll need to do is to get this input encoded according to the labels, which means just for each input, select its corresponding label, right? So the first position here, say x1 is 0, then you pick the label 0 and so forth. So I'm sure all of you remember this. And an evaluator, if they get the gobble circuit and these labels for a particular input, they can just, there's a little process they run to evaluate the circuit. Okay? So that's very standard. What we want is a re-randomizable gobble circuit. Okay? And so we have one more operation here, a re-randomizer, which takes a gobble circuit and, surprise, it re-randomizes it. It produces two things. One is it produces a re-randomizable gobble circuit. It also produces some functions which can be used to re-randomize the encoding function, the labels that I mentioned, right? So now to evaluate, you need the new gobble circuit, and not the original labels, but the original labels modified according to these functions that are produced by the re-randomizer. Okay? So that's how the evaluation now looks. It's the same evaluation process. It's just that what you're taking in is not the actual gobble circuit, but the re-randomizable gobble circuit, and the labels have been accordingly updated. And it's kind of crucial that, so we have the usual security requirements of the gobble circuit are there. Somebody who sees the gobble circuit and the labels have no idea what they are working with. They just get the outputs in the clear. They don't know what the inputs are. They don't even necessarily know what the function is, except some topology of the circuit. But there's another security requirement now for re-randomization, which is that you cannot tell if the re-randomizable gobble circuit you got, along with the updated labels, if they are a result of this re-randomization or if they are fresh. Okay? And there is more to defining this carefully. So this should hold even if you have some additional information about. So this should look like that in a particular sense. You should be able to explain that this re-randomizable gobble circuit is actually a fresh garbling. Okay, so they should look. This could be explained as a fresh garbling, in a sense. Okay, so that is a re-randomizable gobble circuit. So we construct this, but actually it turns out we didn't have to do it from scratch. There's already a construction that was implicit in this work by Gentry, Halevi, and Vaikuntanathan. This was a paper called IHOP or multi-hop, FHE, which essentially did this. They built a re-randomizable gobble circuit. They didn't define it that way, and there are also some, there were some gaps in their definition, which we talk about, or the proof rather, which we talk about in our paper. But mainly, essentially this thing was already there. And they built it from a certain kind of encryption, which we abstract as a key and message homomorphic encryption. Again, the abstraction was not there in the original paper, but this is essentially what they needed. Okay, so we have this object, re-randomizable gobble circuit. How do we use that to build a scales protocol, semi-honest protocol? So here's the general idea. Somehow the circuit will have to be gobbled, and it will have to be evaluated, and there's a bulletin board, right? Evaluated on inputs of the clients. So first up, the clients show up, and they're going to encode their inputs. And how exactly do they encode their inputs? And I'll mention this in the next slide too. They're going to encode it as first message in an OT protocol, okay, in a 2-round OT protocol. Okay, but for now, they just somehow encode their inputs. Then the servers come in. The first server actually creates a gobble circuit. So in this case, the function is public. All the secrets are in the inputs. Right? So the function is public. The first server creates a gobble circuit for that function. Then the subsequent servers sequentially re-randomize this gobble circuit. Okay? And all these gobble circuits are posted on the bulletin board. And now, there are gobble circuits, but you cannot evaluate them because the labels are not there. So somehow the clients will have to finish the OT for you so that the labels become available on the bulletin board. And once it's available, any server can come in and evaluate it. Just one server is good enough in the semi-honest case. It can evaluate the gobble circuit and get the output in the clear on the bulletin board. So, and any subset of these could be corrupt. We do need one honest server here. In this special case, semi-honest setting, even if the evaluator is corrupt, there's no problem. But in our model, we said that there's one honest server in each phase. But yeah, here we don't really need that for the second phase. Okay, so the main question is, how is this going to happen? That these labels will become revealed somehow on the bulletin board. Okay, so presumably each client has only its own input, so presumably it will post the labels corresponding to its inputs. But how exactly would it do it? And I already mentioned we are going to use oblivious transfer for that. So oblivious transfer usually you think of as a functionality, which has a sender and a receiver, and the sender has 2 messages, 2 strings, and the receiver has a choice bit, and the receiver gets one of those strings that it chooses and doesn't learn anything about the other string, and the sender doesn't learn anything about the choice. And there are 2-round OT protocols in the CRS model, the UC secure. But yeah, right now we only care about semi-honest secure, but eventually we're going to use UC secure OTs in the CRS model. So let's just think about that. These 2-round OT protocols work as follows. There are 2 messages, right? So first the receiver speaks. It encodes the choice bit B and somehow sends it as a message. Of course, it hides the message, hides the choice bit, right? And then using that, the sender encodes its 2 strings. So there's a second message it sends, and in such a way that the receiver can decode the chosen string and not the other one. What we need, so these things exist. What we need is an updatable form of OT, because we are going to re-randomize, and we need to correspondingly, we re-randomize the gobble circuit, we'll need to update the labels in a corresponding manner. Okay, so in the updatable OT, there's one more party. It's a third party who has an update function, pi, such that the receiver gets not the SB. It can get SB also, but more importantly, it gets pi of SB. Okay. And in terms of the protocol, when the updater wants to, let the receiver receive pi of SB, so updater is a third party. It has no idea what S0, S1 are. It has no idea what B is. But it can still send an update message which encodes only its pi in such a way that the receiver can then apply a decoding function on its end and get this pi of SB, okay? Without learning anything about pi beyond what SB and pi of SB reveal to it, okay? So again, this object was needed, or something similar in spirit was needed in the IHOP work. So they had something called re-randomizable OT, Jenry Halevi and Vaikundathan, and we need to modify that construction to do what we want. Okay, so now we have that. How is the protocol going to look? So the phase one, first before garbling the circuit, the input parties come in and they post an encoding of their input on the bulletin board, and this encoding is now that first message of the OT, of updatable OT, which encodes the choice bit, right? So think of each party having one bit of input at this point. If there are multiple bits, they'll do it separately for each bit. So they will post an OT first message as the encoding of their bit. And the servers, well, the first one creates a garble circuit. And it also, it's the server is the one with the OT labels, right? It has two labels for each wire. Only one of them should be revealed at the end, but it has both those labels. It sends the OT second message, right? Sends as in it just puts it on the bulletin board. Then the updatable OT servers come, or the re-randomizers come. They have two jobs now. One is they re-randomize the previous garble circuit, post it. The other is they want to update the labels in a particular way. They have a pi that came out of the re-randomization process. They want to apply that pi to the labels, to both the labels. And that's exactly what they can do using this updatable OT update message. So they post the update messages one after the other. So I didn't mention it, but I mentioned it, made it look as though there's only one updater. There's something you can do sequentially, one after the other. So they'll all do it. And the last garble circuit is the one that we are going to evaluate. The labels we need for that corresponds to this entire updatable OT's output, right? Output at the receiver's end. That's the original labels updated and one of them chosen according to this choice. And that decoding can be done by the receiver in the OT protocol, which is our clients. So each one separately does a decoding for its input and produces those labels. And once the labels are there in the clear, anybody can evaluate this garble circuit. Okay, so this is the semi-honest protocol. And it works, as in the corruption model we wanted, as long as the updatable OT and the re-randomizable garble circuits have the right security guarantees, which they do. Okay, so that's all I'll say about the semi-honest version. So it's fairly simple, nothing too complicated, no layers of complications. We do need these primitives, for building a re-randomizable garble circuit and updatable OT, and once we have that, it's not too complicated. Okay, how do you go from here to malicious security? We are talking about, we don't have an honest majority, so it's security with a board. And there are a few different options. The most obvious ones are, we could use generic NISc. That'll be very expensive. Well, nowadays we have snarks, so at least it's not very expensive for the verifiers. So what do I mean by use generic NISc? So we have all these servers coming in and doing their thing, and even the clients doing their thing. We need to make sure they did it all correctly. They can give an IST proofs for that, right? So the servers have to prove something, even the clients have to prove something. And you could make at least the verifier's job easy by using snarks. The trouble is it's still inefficient for the provers. In fact, it becomes even more inefficient for the provers, and you also need strong assumptions. Okay? So not the best option. You could use some sort of a cut and choose. There are all these gobble circuits floating around. You don't know if they are correctly built or not, correctly randomized or re-randomized or not. You could open a few of them and check. The problem is that this cut and choose is kind of inherently a very interactive process. You could, make some of it non-interactive. You could also use, our techniques later to make it more non-interactive, but it's, not going to give you the best solution. Okay, if you want to make it non-interactive. So we go for something else. Essentially, it has some NISK and cut and choose and everything built into it. But now we are going to exploit the re-randomizability of the objects we are trying to prove something about. And those are the gobble circuits, or re-randomizable gobbling scheme, RGS, and the updatability. Right? They have inherently some re-randomizability properties, and we can exploit that to give slightly better proofs. So let me show you that, how that looks. So there's a little simple proof for correct garbling. Okay? So there is a circuit and a gobble circuit. The prover claims that the gobble circuit was constructed honestly by garbling the circuit using some randomness, which only it knows. So how do you prove that? Here is a little proof. So the prover picks a fresh randomness and creates a fresh re-randomizable gobble. It takes a gobble circuit and creates a re-randomization of that gobble circuit. Right? It's not fresh, it looks fresh, but it's actually a re-randomization of the original gobble circuit. Send it to the verifier. The verifier tosses a bit, and in case the bit is 0, what the prover is supposed to do is show that actually this is what it did. It re-randomized the gobble circuit by showing an R prime. This doesn't reveal any secrets because you already knew the gobble circuit. Now this was just freshly re-randomized. Okay, so I can show you this. If the bit is 1, what you need to show is that this re-randomizable gobble circuit actually is a valid garbling of the original circuit. Even though it is obtained by garbling first and re-randomizing, it should effectively be like an original garbling, a fresh garbling of the circuit itself, right? So you have to show that how you can obtain RGC by garbling the circuit C directly using some randomness. So this is the explainability part I mentioned. There should be a way to explain this as being obtained by garbling the original circuit. Okay, so if B equal to 1, you show that. And this is also by itself doesn't reveal anything. You could have certainly garbled a circuit C yourself. But as you would have all seen in zero-knowledge proofs, if you had both these guarantees together, then it does mean something. It means that this garbled circuit, is both a re-randomization of, or rather, there is a re-randomization which is both a re-randomization of this garbled circuit as well as a randomization of this circuit. So the garbled circuit and the circuit come from the same, these two things come from the same circuit. Okay, so if you have seen this kind of stuff in zero-knowledge proofs of Hamiltonicity and so forth, right? So if you have both these guarantees, then you know something about the gobble circuit. Okay, so this directly kind of comes from the ability to re-randomize a gobble circuit. We also need to give proof of correct re-randomization, which is also going to look a lot like this, same thing. So this time we have a gobble circuit and a re-randomizable gobble circuit. The prover has no idea at this point how the gobble circuit was constructed. It only knows that it re-randomizes gobble circuit correctly. It wants to prove to you. Almost the same as the previous proof. Sorry, this is RRGC. So you create a re-randomized, re-randomized gobble circuit. So I should have called it RRGC here. That's when you're going to send. And then you would show that it came from RGC or is a re-randomization of this GC. Okay, so just remove one layer of garbling from the previous proof. Or add one layer of garbling to the previous proof, you'll get this proof. This only gives a soundness of half, right? With half probability, the prover could get lucky, which is actually already interesting, good enough for covert security, and pretty, efficient. So this might be what, in a practical situation with penalties and so forth, this might be reasonable. But you can, of course, amplify by repeating this in parallel. Okay, so we still have, what we have right now is a protocol with, interaction. It's a zero-knowledge proof protocol, old style, it's a sigma protocol, very familiar thing, but it's still not good enough for scales, right? Because we need it to be non-interactive. So how do you change the sigma protocol to something where the prover is ephemeral? They created this thing and they want to give a proof and then vanish, right? They won't be around to answer your challenges. Well, one is you could convert it into an NISc via Fiat-Shamir, but this needs a random oracle, kind of not what we are looking for. And the other option we have is, since we have clients coming back, so even though the prover is ephemeral, will get to speak only once, we can have the client speak a couple of times. So we can exploit that. How? Well, we're going to use something we call a distributed committed index OT. Okay, and it'll make sense when once I finish this. So let me just tell you what a distributed committed index OT is. So now you have multiple receivers. They're going to kind of, together, it's essentially a cut and choose kind of thing. They're going to do something together. This choice, the challenge bit you need to send in the Sigma protocol is going to be generated by these parties together. Okay, so in terms of the committed index OT, there are many of these receivers. They all have a choice bit, C0, C1. They encode that and send their first message. So I'm just describing the structure of the protocol, but the functionality should be clear. The sender has two strings, like an OT. It sends some encoding of those. And then the receivers each post something publicly from which you can reconstruct the chosen string, S sub C, where C is the XOR of all the bits. Okay? So they're together choosing S0 or S1. So this is a cut and choose happening, right? Where the sender is just speaking only once. So unlike a cut and choose where you commit and then you open, here the sender is just speaking once. And one of those things will get chosen. But of course, you don't want a malicious party to be able to choose, because they'll be able to open both of them. So we are going to have we are going to rely on a set of parties. Okay, so our clients in our case, such that if at least one of them is honest, you have no control over which one will be chosen. And so they can all locally post their OT decoding message such that it only reveals S sub C. Okay. So there's some little gadget we can build from scratch on top of 2 round OTs. So we do that. Now what's the use of that? How does that help with turning a Sigma protocol into something non-interactive? Okay, so this, as I already mentioned, this challenge bit in the Sigma protocol is going to come as this committed index. So it's distributed committed index, right? Committed because the index was committed here, index being C, and it was done in a distributed way. So it was not chosen by one party. So that committed index or distributed committed index is going to be our challenge bit in the Sigma protocol. The first message that the verifiers send, or think of, so now, we are turning a Sigma protocol as usually a prover, verifier, prover sequence. What we will have is a verifier or verifiers, prover, verifiers sequence, because we only get one prover message, so prover goes second. Okay, so the first message is going to be from these verifiers. They will send their first message in the distributed committed index OT. The second message is all that the prover gets to speak. So what should they do? So in their mind, they will run the Sigma protocols. There's a first message, and then after the challenge comes, depending on the challenge, there is an answer. So there are two answers. One answer for the 0 challenge, one answer for the 1 challenge. So what the prover is now going to do is one message it gets. It includes the first message in the Sigma protocol as well as the answers to both the challenges, but encoded using this OT. So only one of them can be retrieved, right? It doesn't know which one is going to be retrieved, but that's already fixed, that's already committed, which one is going to get retrieved. It doesn't know it at this point. So that's the one message the prover sends. It has the first message of the Sigma protocol, as well as it's OTing out both the answers to the challenge. And the third message is again from the verifiers, which I'm calling it the reveal message in the ephemeral prover ZK. They are finishing that's the message here, right? So that'll reveal the answer to the challenge in the Sigma protocol. And anybody can now publicly verify. Okay, now that we have that, we have almost the entire protocol here. So first the clients come in, they do two things. One is, so their inputs are encoded using the updatable OT as before. Now they are also going to do their challenges for the ephemeral prover ZK, the committed index OT message, right? So that'll be the first message. That's part of their first message. Then the servers come. The first one creates a gobble circuit, also has to respond to this proof, right? Create its message in the proof, the only thing it'll do for the proof. And as before, it also is doing the labels encoded as the updatable OT message. Then all the servers come in one by one, re-randomize the gobble circuit, they update the updatable OT, and they also locally generate their proof for the, so this can be for different challenges, or I don't know if you can use the same challenge for all of them. Probably can when you're amplifying it. So they prove for each, they are proving, these guys are proving correctness of re-randomization. Okay? This was proving correctness of garbling. And there's also actually some correctness of the updatable OT itself is now secure against malicious parties. Essentially, something similar to this ephemeral prover zero knowledge is going on there, right? Then the verification phase, the clients, they don't have time to read everything that everybody posted here, but they have, each one has enough time to work proportional to their input. That's good enough to send this distributed committed OT, second message or the reveal message, which is a reveal message in the ephemeral prover zero knowledge proof. So they'll all do that, each one working proportional to its input, without looking at anything that happened on the bulletin board. And we need servers, ephemeral servers, to come and verify that these ZK are all good. If anyone sees anything is wrong, they will, raise an alarm, and the protocol aborts. Right? They can post an alarm on the bulletin board, which the client comes and looks, makes sure that all of the servers said OK, and then it decodes. And this will give the labels, for the garbled circuit, for the last garbled circuit, which can then be publicly valid. OK, so, and yeah, this remains secure with the kind of corruption model we want. As I said, you'll abort in case of any inconsistency. The clients will not do this last step if they see any inconsistency, or if the final values are not all the same. We don't, now it's malicious, so some of them could give wrong answers, but at least one is honest. So if all of them say the same thing, you accept the answer, otherwise you abort. Okay, so I think that's pretty much brings me to the end. As I already mentioned, it's hopefully an attractive model for MPC as a crowdsourced service. And many extensions are possible. They're not there in the paper, but these are kind of observations that are not too hard. You could get guaranteed output delivery if you had honest majority. And our ephemeral servers are large, but if you work a little bit, you can make them distribute that work. You can make them work less, each of these ephemeral servers, so they don't have to be linear in the circuit size. But you trade off, you won't have the assumption of only one honest party per phase now. You will have kind of subphases, and you'll need one honest party in each subphase. So you need a little less corruption, or more honest parties, but you can still make these things work. So, I think going forward, what's the main challenge in this for scales is whether it's practical. Can you make it practical? And there are a few bottlenecks, communication, using garbled circuits and so forth. One bottleneck in particular is the KMHE encryption scheme, the key and message homomorphic encryption scheme. We are using something that is already there in the literature, which is not originally created as a KMHE scheme. And that's kind of expensive, though that scheme is expensive. But there's no reason to believe that that's the most efficient KMHE scheme. So maybe you could just find more efficient KMHE schemes, and that'll improve the efficiency of everything. Of course, there could be alternate approaches too. All right, so that's all I had. Thanks.
So questions?
Okay.
Sorry, I did not fully follow. So the proofs from the servers, you said that it follows from something similar, but they can only talk once, right?
Mm-hmm.
So what is kind of the modification, if you could?
So the Sigma protocol had two messages, right? And both those messages now show up as part of this one message that the prover sends. Okay, but of course that wouldn't make sense right now. The first message, you can send it in the clear. The second message is a response to a challenge. If you give both the answers, then you will be revealing your witness. It's a special soundness kind of thing. So you are not going to reveal both, but you will encode them using this in this OT. There is one message in this OT you can send such that only one of those can be reconstructed. So you don't know which one at that point, but you will be guaranteed that only one will be reconstructed. So yeah, we are squishing both the messages in the Sigma protocol into this one message.
Thank you.
Yeah.
So I had a follow-up on the same question. So you mentioned something about public verifiability, where I think this now, the verifier, prover, verifier communication sequence, where the verifiers come and open the OT1 message so that everybody can verify. So in that case, so this was for the ephemeral prover ZK,
Okay. So
where we switched the Sigma protocols kind of message from prover, verifier, prover to verifier, prover, verifier. So in that case, the last message from the verifiers are going to be opening the OT1 message, which committed to the bit.
Their messages in this distributed committed index OT. They're not opening. This is, carefully designed thing such that you will only reveal this thing. They're not revealing their choice of, we don't really care about them picking up, each one is not picking up S0 or S1. Right? They're together picking up this S sub C, and only that will get revealed. So you need a little gadget to make that work. It's not immediate.
And there are no guarantees about it being publicly reconstructed because one of the clients could just not open, in which case...
Yeah, so you need this also to be secure against malicious corruption. Yeah, of course, again, cause a bot, they shouldn't be able to bias the whole thing. So this XOR, they shouldn't be able to bias, right? It'll actually be an XOR.
Thank you.
Yeah, I think.
So this zero knowledge proof for garbling, are there any benefits have you tried using it in two-party secure computation itself? Are there any advantages to that technique?
You'd probably have, but you'd probably have better advantage because KMHE makes the garbling itself a little inefficient. So if you just wanted non-re-randomizable garble circuits and wanted to prove correctness of that, I would think there will be better options.
But if you wanted reusable garble circuit, then with that
Re-randomizable.
Sorry.
Yeah, then, this is one of the few places where it has been used, right, so far. The IHOP paper had it, but they didn't have any, it was all semi-honest. But yeah, this is the next place where we are using re-randomizable garble circuit.
Okay, so I have one very quick question. So the re-randomizable garble circuit is what requires this assumption,
KMHE, yeah.
Okay, so
KMS
have you tried to improve on that assumption, or?
Not, we have tried a little bit, but without any success. But I'm sure we have not exhausted all possibilities.
Okay, so actually, like getting re-randomizable garble circuits from better assumptions, or
yeah.
like
So
more
assumptions-wise, it's just DDH. Okay, you can ask for post-quantum security and so forth.
but computation-wise, I guess improving
Computational
it.
efficiency is, I think, the bigger practical issue.
Okay, okay. So we will take other questions offline because we are running out of time. So. Okay, so it's my pleasure to introduce the next speaker, my dear friend and a rising star in the community, Chenda Lu Zhang. He's a co-head of the Information Systems Lab and Blockchain Lab at Luzerne University of Applied Sciences and Arts. He is also a research scientist at Web3 Foundation, and he very happily glides between several areas like cryptography, distributed computing, and blockchains. And his recent works revolve around designing efficient protocols for secure computation over asynchronous networks, secure computation over dynamic committees, consensus protocols, and peer-to-peer networks, some of which are also my favorites. Previously, he was a postdoctoral fellow at CMU and NTT Research and did his PhD at ETH Zurich. So the stage is yours, Chenda.
Okay, thank you. Thanks for the very nice introduction, very generous introduction. And thanks for the invitation, and also thanks to all the organizers. It's been so far an amazing workshop, and I'm very honored to be here. So today I'm going to talk about multi-party computation with dynamic committees. So yeah, I have a couple of slides on introducing MPC, probably for the 5th time in this workshop. Usually in the setting of MPC, you have a fixed set of parties, right? And parties, 3 of them are corrupted. They communicate over, let's say, a complete network of bilateral channels. Sometimes we also have broadcasts. We want that all the honest parties obtain the correct output, right, which is a function of the private inputs. And of course, the adversary shouldn't learn anything beyond the inputs and outputs of corrupted parties. So all this idea of dynamic committees and so on, at least from my limited knowledge, this came from the idea of trying to scale MPC, right? And maybe this was partly motivated by blockchain applications. At least some people say that there was the question, can we scale MPC to lots of parties, let's say, I don't know, hundreds of thousands, even millions of parties or something like this. This is, of course, a very ambitious goal and a little bit different from the traditional scenario that we imagine of MPC, where there is like a handful of parties executing a very large circuit, right? And of course, one approach, and this was actually known already a long time ago, to help with this was, well, I'm going to select a committee, right? Committee of representatives for the MPC protocol. Hopefully this committee kind of correctly reflects the overall population. This means that, let's say, I have this small committee of logarithmic size in the number of parties, and hopefully the corruption threshold within the committee is similar to the corruption threshold in the overall population, right? And then you can essentially just delegate all the computation to this committee, right? So you have, let's say, all the parties, they have inputs, they distribute the inputs to this committee, and this committee goes through a sequence of steps, right, to perform the computation. This is essentially like, you know, like the client-server model, but the servers is just like this set of committees. And then they perform the computation, and at the end they obtain the output, which is again distributed to the parties that are supposed to obtain the output, right? So you can select a single committee that performs the computation, and that kind of helps with scalability. And of course, the problem that immediately arises with this question is that an adaptive adversary can, of course, corrupt the whole committee after it is revealed. For example, you just wait until they send the first message, and whoever is speaking, then you just go and corrupt them, right? And then there was this at least in the blockchain community, there was this paper by Chen and Mikali, which is essentially had this nice idea, which they didn't call MPC with dynamic committees or anything like this. They called it player replaceability, right? This was like a term that was already there in the consensus and distributed computing literature. And the idea was that, well, why not just change the committees, right? Instead of having one single committee, I'm gonna just change the committee at every step. And hopefully if they speak only once, then the adaptive adversary is kind of like too slow to harm the protocol, right? Like if you already send your message and then you become adaptively corrupted, then you're like, oh, well, I already did my job. You don't really harm the protocol, right? Um, and how did you select the committees? At least in this Algorand paper and in some of these other consensus and blockchain papers, they were like, okay, I'm going to just choose the committees using a VRF. It's a verifiable random function. And this essentially guarantees that each party is chosen, let's say, independently with a certain probability. And essentially this guarantees that the corruption threshold within the committee is going to be essentially the same as the overall population by applying like Chernow bounds, right? But of course, then there is the question, this is kind of like one of the difficulties. So say there are two committees, C1 and C2. Committee C1 has to send a message to committee C2, right? But when C1 is speaking, maybe C2 hasn't been revealed yet, right? And of course, at that time, with all these player replaceable protocols, this was not really solved in a satisfactory way, I would say. And the point was that it turns out that if you look at this, or if you work in all these consensus protocols, what happens many times is that all these messages are actually public, right? You just need to count votes and so on, and then if you receive enough messages, you proceed and so on. So actually the messages that C1 needs to send, most of the times are public, maybe they are signed and so on. So there was actually no difficulty in sending messages from C1 to C2. C1 could just simply send to all the parties. And that's kind of like why these player replaceable protocols worked. But now, like, what about private messages, right? And this is kind of like in the context of MPC, these point-to-point channels that go from committee 1 to committee 2 are typically need to be private, right? And how do you send this private message to committee 2 without knowing who committee 2 is? And this is actually much harder task now. And I actually had a paper before all these models. We didn't really solve this problem. We didn't know. We just kind of pushed it to the setup. We said, well, in this paper we're thinking, yeah, we need kind of an MPC protocol. This was also in the context of consensus. We had to design some efficient MPC protocol to help to build consensus, which is kind of strange, right? Because usually it goes the other way around. But we were saying, in that MPC protocol, we needed some committees to speak to the next committees, and then there were some private messages, and this was kind of like not so easy to do. We just said, okay, let's just assume there is a trusted party that elects these committees, and then just gives keys. And the most trivial thing to do this is just to use public key encryption, right? The trusted party generates these two committees, and then gives publishes public keys and gives secret keys, let's say, on behalf of each party in the second committee. He gives the secret keys to the first committee, right? And then now if the first committee needs to send a message to the second committee, then you just encrypt under that key, right? So that's kind of like what we did there. And actually a lot of people had like many wonderful ideas that implemented this trusted party, right, in much more clever ways. And there's been a great line of work focusing on this question: how can you send these private messages to the parties that you don't know? Perhaps the first work that I'm aware of that addressed this was the work by Benhamuda et al., right? Can a blockchain keep a secret? They presented a protocol that works, I think, like for n/4 corruptions, right? And then this was later improved to optimal resilience in the random index PIR paper. If you want to know how it works, go to Ivan's talk a few days ago. I think he talked a little bit about this. And then there were other ideas, follow-up works in this direction. I'm not gonna talk about this. But let's talk about how you actually formalize this MPC with dynamic committees. With these player replaceable protocols, there was no actual model, right? This was more like a property of the protocols. Parties only speak once. There was no no proper formalization of what player replaceable actually means, right? And there were some initial formalizations of MPC with a sequence of committees. And I want to mention a few of them. One of them is the framework of you only speak once. I really like this formalization because it essentially divides the design of the MPC protocol into two parts, right? If you want to build an MPC with dynamic committees, then you can first, this appeared at Crypto 21, I think. So first, you build a protocol that implements this trusted party that I kind of talked about, right? And this trusted party will be in charge of selecting the committees in such a way that the committees have like a similar corruption threshold, right? But also, they call it role selection, but I like to call it role selection and communication, right? Because you also need to build this private communication between the committees, right? And then on top of that, after you build this role selection mechanism, or role selection and communication mechanism, then you can just build an MPC protocol assuming this, right? And this is kind of a similar architecture than normal MPC protocols. You first kind of build the network, right? How to like secure message transmission protocols and so on. And then on top of that, you build the MPC, right? So if you kind of can decouple these two protocols and think about, for example, the MPC without having to think about how you send messages to the future and so on, right? And at least in the initial paper, they said, okay, I think that at least the spirit was how hard can the MPC be? And in the Yoso MPC protocol, they show that it's enough that if you have this role selection mechanism, that the security of the MPC protocol is against this random adversary, right? Because the idea was that if you select these committees at random, then a worst case adversary essentially cannot do anything better than a random adversary, right? And every committee may be different. I have to say here that even though kind of like this Yoso MPC protocol was against a random adversary, as far as I know, all the Yoso protocols also hold against a worst case adversary, right? So this is not an essential part of the framework, to the best of my knowledge. So the second framework was that appeared also in parallel at the same conference was the fluid MPC protocol. It was by Chuduri et al. And it was kind of like shared a lot of similarities, right? Although it came from a different motivation, right? I think their motivation was more like, you know, you select these committees and the idea is I want to distribute the resources, right, and so on. Rather, they didn't focus so much on adaptive corruptions. But formally speaking, the two models, at least in my view, share some similarities. And they were kind of like a bit more concrete with the role assignment mechanism. And they were saying, okay, instead of having like this network, I'm just going to assume that there is this network that is already there, right? And the network that they have is that every committee I can send to every committee in the next round, right? So a committee I has already channels established to committee I+1. I don't tell you how these channels are built or anything, right? I just say, imagine there is a sequence of committees. Each committee has up to T corruptions, right? And imagine also that I already have these channels. Every committee I can talk to committee I+1, and then I can kind of build an MPC on top of this, right? So essentially, it's kind of like the second part of the Yoso, right? But for like a specific network somehow. And after that, there were some other variants of MPC with dynamic committees. There was scales that Manoj just talked about. To my limited understanding, this is kind of like Yoso, but clients can speak several times. Of course, there are also requirements on the efficiency of these clients and the servers and so on, right? There was also this layered MPC. I'm actually also co-author of this paper. But it's actually the same as this fluid MPC. It's just maximally fluid, right? We just gave it like a more succinct description. And there is the recently a recent model also that there is like a PASO. This is also kind of like related to YOSO. You can think about it as a sequence of committees. It's just that the committees have size 1, right? So it's kind of like a restricted restricted description, I guess. So there are n parties in total. They speak in sequence 1 by 1, and you can corrupt T of the parties, right? So you have all these MPC with dynamic committees, lots of models, right? And at least when I got into this area, I was like a little bit confused, right? Like why there's so many names, so many models? How do they relate to each other, right? And that's why I also like this abstract YOSO kind of modularization, because it essentially says that if you want to build an MPC with dynamic committees, then you first build this protocol for committee selection and communication. And then the observation also, which maybe some people know, maybe not, is that after you have this committee selection stuff, right, and the channels are already established, you can actually contribute to the community of MPC with dynamic committees just by, without needing to think about whether the parties join and leave or and stuff like this. You can just build an MPC which is completely standard with a fixed number of parties. It's just that the communication pattern is restricted, and the adversary structure is also like a restricted. So let's go through some examples. So this would be like the maximally fluid, or MPC, or we call it also layered MPC. So you can have, let's say, a total of n times L parties, just a normal MPC protocol, right? And they are organized in these L layers. Each layer has, let's say, n parties. The first layer, let's say, are the input clients, right? The parties that have input. And then you can only communicate to the next layer. So layer I communicates to layer I plus 1 via these private channels. I don't care how these channels are built, right? The channels are just there. And they can also broadcast, right? This is kind of like a classical MPC model. So layer I here is kind of restricted. Layer I can only talk to layer I plus 1, and they can broadcast. And then you just follow this communication pattern, which is restricted over layers. And also the adversary structure is also restricted in the sense that the adversary can corrupt up to T parties per layer, right? And you can just build a protocol like this without thinking whether the parties rotate, join, and leave, and so on. Don't need to think about any models, and like this, you actually already obtain like a maximally fluid MPC. So the YOSO MPC, actually, if you take this view, at least under my interpretation, you can also think about it this way. It's just that you also have like a few extra channels. So instead of having these direct channels from committee I to committee I plus 1, then let's say this role assignment mechanism that they built, you also have channels that go kind of farther away to the future. So for example, party 1 can send something to party 3, or to party 1 in layer L, and so on. And you can also build like a standard MPC protocol in this model with this communication network, and then you would obtain like a YOSO protocol. Okay. At least that's my understanding. Of course, they said in the original paper random corruptions, but you can also say, well, I'm going to build it with worst case corruption. You know, would also consider it YOSO. And then one question that I asked, it was is it actually stronger to assume these channels to the future, right? Like here I have these orange channels. Here I don't have these orange channels. Are they actually the same somehow? And if you look at it from the first instance, then you'd say, yes, maybe. So if I want to send a message from party 1 in layer 1 to, let's say, party 1 in layer 3, and this is like a secure secure message, right? Then you can actually just use a secure message transmission protocol, right? As we all know. And then you say, and build this orange channel using the blue channels, right? And the guarantee would be that if let's say P1 and P3 are honest, right, is a secure channel, then the receiver will get the input of the sender, and yes, and this message is private from the point of view of the adversary, and you can use, let's say, just some error correcting code to achieve this. You get your input, you encode your input into all these different code words, and then the middle guy is just forward to the third guy, right, who can just decode with error correction, right, and of course this satisfies the property that we wanted to, right, assuming that the middle layer doesn't have too many corruptions and you can actually perform the error correction, right. You can actually also do this at 2n/2 corruptions using some sort of like a robust secret sharing type of thing, right? If you add on top some authentication mechanism, right? And then for a while I was thinking, yeah, then actually like Fluid and Yoso are like essentially the same. But one subtlety that arises when I was trying to make this proof work was that here, at least in this protocol, if the sender is corrupted, he can distribute these code words in such a way that he can still choose the message during the second layer, which is kind of fine. And then there was this subtlety, at least in the original Yoso paper, the information theoretic protocol, that did assume somehow like channels that are slightly stronger, in the sense that even when the sender is corrupted, the input of the sender is decided at the beginning. And you can think about it as in the context of blockchain, if you kind of broadcast some ciphertext or some commitment or something, you are already committed to your input from the beginning, even if you are a corrupted sender, right? And then I was thinking, okay, is it actually like that difficult? And to my knowledge, it's actually not so easy to build these adversary committing channels, right? To make the adversary commit to the channels from the beginning, even if you assume these direct channels between adjacent committees. And at least in my view, if you don't have setup, this is actually pretty hard, right? Because at that time I was trying to do it information theoretically. I think this is probably even impossible, right? But yeah, happy to discuss. So in this sense, if you assume these adversary committing channels, then you'd say, okay, also MPC under these channels would not imply this fluid MPC, although the other way it would hold. If you would have like a variant of Yoso, where the channels are non-committing, then I think this would actually be equivalent, the two models. If you look at this graph thing, then you can also talk about this PASO stuff. And PASO would essentially be, you have these L parties, one party in each layer. Every party can talk to the future, right? Or broadcast something. Yes, stay for the next talk. There is like a nice talk about PASO. And I had a little bit of difficulty here actually yesterday night when I was preparing the slides somehow. It might not be super accurate, but I was trying to build like a slide, at least for myself, right? How do you relate these models? And of course, fluid and layer are essentially the same, right? And by the argument before, if you have a protocol that only uses direct channels, right, as in the maximally fluid setting, then this would also be Yoso, right? The other way around, at least in a version of Yoso where you have the committing channels, is not clear to me that you can get a fluid protocol from Yoso. And then you have the implication from Yoso to scales, just because the clients can speak like a few times. And then the relation between PASO and Yoso is kind of like I put it in dotted lines because this is almost like a trivial implication, right? In PASO, you just have committees of size 1, so essentially, like, yeah. If you translate it into YOSO, all the committees would essentially be honest, right? So it's kind of like a trivial statement. And then I did a little of digging, right? And this area has been so active in the last few years, and I'm sure I'm missing some or a lot of the papers. I tried to focus on like fluid and YOSO, although there is also like a bunch of works on scale, also a bunch of works on PASO. There was also some prior works. There was this CSAR, right, and other papers like pre-YOSO and so on. But yeah, this is the list I could come up with. And there is the original papers by let's say Chuduri, right? That was the original paper in the fluid setting. They gave this N/2 protocol in the security with abort setting, computational. And at the same time, there was the YOSO paper, which achieved a stronger security guarantee, right? It was guaranteed output delivery. And they also gave an information theoretic protocol. And for a while, at least when I was talking to people, people were thinking that doing guaranteed output delivery in the fluid setting was going to be pretty hard or almost impossible. And we proved that this is actually not true. You can also get perfect security and statistical security in the fluid setting. And I'm going to talk a little bit about this. And then there has been some nice works in the YOSO setting, improving the round complexity and also relaxing the setup assumptions. And there is also a very nice recent work that says that you can achieve guaranteed output delivery against a very large number of corruptions if you only have, let's say, one committee that has honest majority, right? That's also very nice work. So for now, I'm just going to talk a little bit about these results in the fluid setting, which also translate to the YOSO setting, right? So what is the recipe for a layered MPC? Actually, this is also the recipe for the information theoretic YOSO protocols. You first design, okay, maybe not the first step, because in YOSO you already have the channels for free. But at least in the layered MPC setting, you can only talk to the next committee. So the first question is, how can I talk to further committees, right? And I'm not going to talk about this because this is kind of the easy step, right? It's just like if you use like error correcting codes, then you can essentially talk to the future. It's just that the communication complexity kind of explodes at every step because you need to share and reshare and reshare and so on. And that's why, at least one of the main reasons why all these fluid protocols or maximally fluid protocols in the information theoretic setting and the perfect security setting are so inefficient is like because the future messaging is actually quite heavy, right? But anyways, let me just take the YOSO approach and assume that I already have these channels to the future. These channels are not going to be committing, right? So if I send to let's say a layer that is 100 steps away, the adversary can decide on the message that the sender is sending if he's corrupted up to the last layer, right? He can wait until the layer 99, let's say, and look at all the intermediate messages and only then decide, actually the message that I wanted to send was this one. And this actually makes a difference if you think about, let's say you want to do some sort of a Sigma protocol. The first message goes through, right, travels far away, and then in the middle you generate a challenge. And of course you don't want to generate, now you don't want the adversary to be able to choose the first message based on the challenge that you chose in the middle. And that was essentially the reason why the information theoretic YOSO didn't go through with these non-committing channels, right? So I'm going to talk about a little bit about these distributed commitments and and the verifiable secret sharing. So what is a distributed commitment? This is essentially like a commitment in the distributed setting. Some people know it as weak secret sharing. And the idea is that, okay, there is this dealer in some layer, let's say layer 0. And at some point in the future, there is another layer of shareholders. Each one will have a share, and at that point, we just declare the sharing phase complete. There are two phases, share and reconstruct. And the properties that we want are that if the sharing phase succeeds, then you can only reconstruct one value. This is exactly the same as a commitment, right? As a normal crypto commitment. And then you can later reconstruct, and you can actually reconstruct the value if you are guaranteed to reconstruct the value if the dealer was honest, right? But if the dealer is corrupted, just as in a normal commitment, then the adversary can prevent the reconstruction and kind of like abort it, right? So you can actually just reconstruct bottom. And privacy just means that the secret was not revealed during the sharing phase. If you didn't start the reconstruction, then the adversary has no clue what the secret is. So I know I said I was going to talk about all these information theoretic and perfect security protocols, but I actually wanted to talk about like a protocol that uses commitments, because that's kind of much easier to explain. But if you want to know how to do this information theoretically, you can come and ask me after the talk. So if you would have normal cryptographic commitments, actually building a distributed commitment is quite easy. So it's just like a one-round protocol for the sharing phase. You just do kind of this Feldman approach, right? So you create this degree T polynomial, right, based on your secret, and then you have like these T plus 1 coefficients. First coefficient is the secret, and then you have F1, F2, F2, Ft. And then you just broadcast, using a cryptographic commitment, you just broadcast the coefficients, right? And send evaluations of this polynomial to each of the parties. So at that point, after the sharing phase, each party has 1 point in this polynomial, and everyone sees all these commitments to the coefficients. And if the commitments are homomorphic, let's just think about Peterson, something like that, then when you receive the share, you can actually check that whether you got the correct share, right? You can check it against the commitment. And moreover, if the parties get like a good share, they know this lies on a degree T polynomial because there were only these T plus 1 coefficients committed, right? So that's the sharing phase, very simple. And then after that, you can, in the reconstruction phase, everyone just publishes the opening information of these commitments that they got during the sharing phase. And if you get T plus 1 correct shares, then you can interpolate the polynomial and output the secret, which is the polynomial evaluated at coordinate 0, right? And here the idea is that why are you committed? This is very easy to see because the dealer actually publishes these cryptographic commitments, right? So the polynomial is actually, these commitments actually commit the dealer to a value or to a degree T polynomial. It's just a matter of how many of these parties actually receive a share. If you get a share, you can check it against the commitments and then you know it's a good share. But if you don't get a share, there is nothing that you can do here, right? It could be that not enough honest parties get a share, and then in the reconstruction phase, nobody gets enough correct shares, and that's why you just reconstruct bottom in that case, right? So the adversary, even after, if the dealer was corrupted, the adversary can later in the reconstruction phase still abort the protocol because the parties didn't have, the honest parties didn't have enough shares. So okay, this is a description of the protocol. I think it's simple enough that we can understand. So how do you do like a verifiable secret sharing based on this distributed commitment? So verifiable secret sharing is essentially the same as a distributed commitment, with a slightly stronger guarantee. I didn't write binding here, okay. So after the sharing phase succeeds, the adversary cannot abort, right? So there is one committed value, and then if you run the reconstruction phase, you actually get the committed value. The adversary cannot abort, right? So that's the only difference between VSS and distributed commitment, but like VSS is strictly stronger. So how does the verifiable secret sharing works? And there is this very easy recipe or this like quote. I don't remember where I heard this for the first time, but there was essentially, if you want to build a verifiable secret sharing, then you can essentially nest 2 instances of weak secret sharing or 2 instances of distributed commitment. And you can think about it like this. So the dealer has a secret, and he essentially follows this distributed commitment and creates these commitments, right, to the coefficients of this degree T polynomial. And then in the first step, you can do the same. You say, I'm going to send the shares to the first layer, right? Every party gets one of the shares. And now the parties can, again, just like in the previous protocol, check the shares against the commitments. But now the danger is kind of that every party holds a full share, right? And that's kind of like what made it possible for the adversary to abort the reconstruction. And the idea of VSS is like, I'm gonna like reshare each share, right? So if each share is actually held by all the parties, then it's not so clear that the adversary can now just withhold its share and not contribute, right? So 1 VSS equals to 2 nested distributed commitments. Okay, this here you can check, right? And what we do is now each of these coefficients, you can think about it as the full polynomial that you share in the beginning. You reshare each of the 2 the coefficients, right? And how do you reshare it? You do it using a distributed commitment, but where the recipients are the second layer, right? We are in the first layer. The first guys will speak in some way, right, that I will define now. So you do this weak secret sharing or distributed commitments towards the second layer, and we have these channels already established from the previous abstraction. And now the second layer essentially has this property that every coefficient is held by all the parties, essentially, right? Because I just did a distributed commitment on every coefficient. And you can think about it as every share is held by all the parties. If you have kind of like the coefficients, you also have the shares. And the idea here is that now in the first layer, some people will be happy with the share they receive from the dealer. And some people will not so happy with the share they receive from the dealer. Maybe it doesn't pass the check against the commitments. Maybe they didn't receive a share and so on. So the guys in layer C1 will just broadcast a complaint. Those that didn't get a good share, and then the guys in the layer C2 will reconstruct the bad shares, which they got from the dealer, right? And the good shares, you can again like redistribute to the shareholders, right? If I got a good share in layer C1, I can just use the distributed commitment protocol to reshare my share and give it to the shareholders. And the idea here is that for each honest party, right, either they got a good share, let's say in C1, each honest party, either they got a good share, in which case they managed to redistribute the shares to the shareholders in the last committee, or they didn't get a good share or no share, in which case the share was reconstructed by the C2 guys. That's kind of the idea. So the shareholders here in the end get enough information, right? If the VSS succeeds, you know that that all the shares by honest parties are essentially out there, right? Either the dealer was corrupted and some of the shares have been published, and the other shares have already been distributed, and this will be enough in the reconstruction phase to robustly reconstruct the secret and prevent this abort attack that I talked about in the weak secret sharing. But yeah, anyways, this is kind of like how we do it. In the information theoretic setting, is substantially more difficult. This actually works also for n/2 corruptions. Yeah, in the information theoretic setting, you need to like do a bunch of more steps. Especially in the statistical setting, you also need to do this information checking and like a few more steps. Here is some description of the protocol, but yeah, the key takeaway message is like VSS is 2 nested invocations of weak secret sharing, right? That's kind of the recipe. And the conclusion of this talk is kind of like, yeah, the YOSO framework is very nice. You can contribute to this nice area of MPC with dynamic committees without really understanding the model, right? You just focus on the second part. You do standard MPC with a restricted communication pattern and adversary structure. And actually, that's how I started getting results in this area. So I encourage especially first-year PhD students that would like to work in the YOSO or fluid MPC. They don't need to, okay, it's nice to read these papers, but they can already contribute without reading these models, right? That's kind of the message of this talk. And with that, I finish the talk. Yeah. Happy to take questions. Yeah.
Yeah, thanks, Chinda, for at least the first part of the talk, because I also echo your statement that during the corona time, almost in every few months, we have been bombarded with different models, and we were scratching our head to understand the relation amongst them. So it was very nice, that part of the talk. Yeah, questions? Yeah.
Sorry, anybody have a mic here? So as I understand it, you define the security on the right here.
Oh, okay.
Left,
There.
sorry. So as I understand it, you define security in the standalone model because it's just standard MPC with restricted communication and adversary structure. So like with KLR, you can derive like UC security, but then that breaks the communication pattern. So do you think like with KLR, you can do like the synchronization like within each committee itself, or like from one committee to the next committee and still get UC security?
You are asking whether it's hard to model this in UC, the standard MPC?
No, so I'm saying like instead of modeling it in UC, like can you derive like a similar like KLR style result where the communication pattern is maintained? Because KLR doubles the round complexity, right?
Yeah, maybe, probably. Yeah, I guess so. Yeah, but I didn't fully follow the question somehow. Like you are saying that whether modeling this in UC is like, I mean, I don't really. Okay, so modeling this in UC, I don't think there is like any subtleties here.
No, the question was, can you like derive UC security for free, like assuming?
Okay. Well, I guess if you have a straight line simulation, then that's essentially, in my experience, UC secure. Yeah, and most of the cases, at least, yeah, if the protocol is, or at least that's the saying, if the protocol it has perfect security, then you can get UC security, and if it's information theoretic, then yeah, most of the cases it's also UC secure. There is some subtleties there, but yeah, probably, yeah. Mm-hmm. I think you should get UC security at least in some cases, yeah.
Thank you.
I got confused about the VSS you mentioned.
Okay.
I got confused about the VSS because you said if the first committee gets bad shares, the second committee will reconstruct the bad shares. But what they have is distributed commitment. I thought, why can't that reconstruction fail?
This the reconstruction of the
bad shares.
C2 guys. Yeah, if anything fails here, you can actually disqualify the dealer, and then just say the sharing phase failed, because that can only happen if the dealer is corrupted. Yeah.
Okay.
Okay, so any other question? Okay, so if not, then let's thank the speaker again. And
Thank you.
okay, so I guess we break for the coffee and join back in 20 minutes.
Do I just put it somewhere? Okay. Is this okay? Okay, cool. Thank you. Let me see. Oh, okay, I see. Thank you. Cool. Thank you so much.
Welcome again to the next session. The first talk in this session is by Lisa, who is a PhD student at CMU, and she will talk about efficient distributed randomness generation. Thank you, Lisa. Please, stage is yours.
Yeah, thank you so much. Hi, everyone. I am Lisa, and this is a joint work with my awesome collaborators, Chenda, Zhao, Pratik, and Aravind. And to start things off, let us recall why we need randomness in the first place. The answer is that randomness is truly used everywhere, from ensuring fairness during the green card lottery to its usage in the clinical trials and audits to numerous applications in the blockchain space. And all these protocols require randomness that satisfies a few important properties. First of all, it shouldn't be possible to predict the randomness before it was generated. Second, no one should be able to bias the randomness. And finally, a lot of protocols profit from randomness, which can be seen by everyone. And this is precisely the type of randomness that we achieve in this work. And to obtain it, we will be working in a model called Parties Speak Sequentially Once, or PASO. The model has been proposed at Crypto 2022 by Nielsen, Ribeiro, and Obremski. And it was inspired by YOSO, or You Only Speak Once, which was introduced by Gentry et al. The model is tailored to the randomness generation setting, and as a motivation, we can consider the following scenario. Let's say we would like to have a long-running service which emits public random bits. As the service is long-running, we would like to support parties that can dynamically join and leave the computation. And at each point in time, only one party needs to be online. Finally, we would like to protect against some amount of corruptions. Okay, so a little bit more formally, we will have n parties, which are activated one after another. Each of these parties will have its own source of randomness, and each will output a public message and also send private messages to future parties. So, for example, P2 can send messages to P3 onwards. The adversary can corrupt any T out of n parties. Depending on how the message forwarding is done, we will consider two different adversarial models. So let's say we have a party PI that wishes to send a message M to a party PJ. And let's say that this party Pj is adversarial. In the execution leaks model, we will have the adversary receive M upon the execution of Pj. And in the sending leaks model, the adversary will be able to receive M as soon as Pi sends it. Either way, in both of these models, our goal will be to generate an unbiased public random bit. Okay, so in terms of prior work, we know results from the information theoretic setting, where Nielsen, Ribeiro, and Obremski proposed protocols which require 60 + 1 parties in the sending leaks model and 5T in the execution leaks model. Unfortunately, the problem with these protocols is that they required exponential communication and computation complexity. And in this work, our goal was to design efficient distributed randomness generation in PASO. And towards obtaining it, we switched to the computational setting. We still would like to optimize the required number of parties and also minimize the assumptions. And in the rest of this talk, I will be addressing this question. We will start with some strawman approaches, and then I will introduce one of our protocols, the one that is based on commitments. And finally, we will briefly study some lower bounds in the sense that we will see how many parties you need for PASO randomness generation. Okay, so let's start with some initial ideas. How could we possibly obtain an efficient PASO randomness generation protocol? Well, the first thing that probably comes to mind is that we could take any stateful randomness generation protocol and transfer it into the PASO setting. And by transfer it, I mean we can simply linearize the protocol. So we can implement each party's behavior over error rounds in the stateful protocol using R+1 parties that will be speaking one after another in the PASO model. So what it means exactly is, like, let's say that the first party that corresponds to P1 will execute the protocol for P1's first round and also pass state to the sort of next instantiation of P1, which will in turn execute the second round of the protocol and pass state to the third instantiation of P1, and so on and so forth. So clearly this works. This will give us a randomness generation protocol in the PASO model. However, the problem with this is it results in a pretty bad resiliency. So we are still able to tolerate only T corruptions. However, now we require not only n, but n times R+1 number of parties. Okay, so can we do better? Well, the next approach would be to follow the well-known commit and reveal paradigm. And in the PASO setting, it looks roughly as follows. We have T+1 so-called dealers. This will be the parties that contribute randomness. And we will have two T+1 parties who help to reveal the contributions of these dealers. And for simplicity, let's say that we focus on the execution leaks model. Okay, so what do the dealers do? Well, they simply commit to a random value and send an opening to each recipient. Each recipient can publish then all the openings that it received. And let's say that we would like to count the dealer's value if and only if the majority of the receivers reveal the correct opening. The final result will be then the XOR of all RIs that come from the valid dealers. The intuition is that since at least one dealer is honest, so the randomness should be good, right? Well, unfortunately, this is not the case. And to see this, let's say that, so like there's a problem that a collusion of a dealer with a receiver can unfortunately bias. To see this, let's consider an example. So let's say that we have a corrupt dealer D3 and a corrupt recipient R5. So what do they do? Well, let's say that D3 commits to the input bit 1 and sends its opening to the parties R1 and R2, which are honest, by the way, but not to the honest parties R3 and R4. What happens? Well, R1 and R2 will obviously open all the values, including the value from D3. But R3 and R4 did not receive anything, so they don't open. And now the R5 can see all the info and can decide whether to open its opening from D3 or not. And basically it means that D3 plus R5 can choose whether to flip the result submitted by the honest dealers D1 and D2 or not. So essentially, they fully control the bit. Okay, so what we need to do is we need to somehow prevent this conditional abort attack. And in our work, we have a lot of protocols that do this in various different ways. And for this talk, I would like to introduce you the one that works with commitments. Okay, so we would like to follow the commit and reveal approach, but prevent the conditional abort attack. Meaning that we would like to ensure that if the sharing succeeds, then the secret will be reconstructed. And towards obtaining this, we will use something which is called, which I would call for the purpose of this talk, weak distributed commitment. What do I mean by this? Is, well, intuitively what we would like to have is we would like to have a protocol between a dealer and a subset of subset S among the overall set of parties, such that the dealer's value is hidden from everyone except from the parties in S, and that it also satisfies certain binding properties in the sense that if at least one party in S is honest, then the sharing will be either aborted or the value will be fixed. At the same time, again, if anyone in S is malicious, we would like to either abort the sharing or the honest dealer's value will be reconstructed. And additionally, if everyone in S is honest, then we have the guarantee that an honest dealer's value will be reconstructed. Okay. So let's take a look how we can construct such a distributed protocol. So it's actually pretty simple. We can have a dealer commit to the random value, or actually we can have the dealer commit to the secret S. And additionally, the dealer will send the opening to the parties in S, which are, for the purpose of the stock, parties P1 and P2. Okay, so now party P1 and P2 can individually check whether the opening corresponds to the commitment that was published. And if they are happy, then they forward the, okay, like if it was a stateful protocol, then we would have been done. This would have been the end of the sharing phase. But I will just show you how to do the reconstruction phase in the pastor model. So essentially, P1 and P2 will both forward the values that they received to the reconstructors R1 and R2, because they cannot speak once, so they will just do it right now. Okay, and R1 and R2 can then simply publish the values that they receive, and then you can reconstruct given any valid opening that was published by R1 or R2. Okay. However, if anyone in the set S, so like if either P1 or P2 complain, then we simply abort the protocol. Okay, so why does it work? Well, intuitively, if at least one of the PIs is honest, then we know that PI will check the value that it received. So it will also check the opening. And then if it was happy, okay, like if it was not happy, then everyone will abort because PI will complain and everyone aborts. Otherwise, PI will send a valid opening to everyone in the reconstructors, from the reconstructors, and if at least one of the reconstructors is honest, then, well, everyone will be able to reconstruct. This ensures that the value will be fixed during the sharing with guaranteed reconstruction. Additionally, if all of the PIs are honest, then we know that the honest dealer's value will be reconstructed because nobody will complain and everybody will send the openings to the reconstructors. Okay, how do we use it? Well, again, we can compute the coin as in the Strawman commit and reveal approach that I introduced before. So we will compute it using an XOR of RIs, where at least one of the RIs will be honest and unpredictable before reconstruction, and the adversarial RIs are fixed before the reconstruction. How do we get it? Well, the idea is to generate multiple random coins using different dealers and different sets of parties. So essentially what we would like to achieve is we would like to have one honest RI survive until the reconstruction phase and be hidden before. What do we need to do for the purpose of the distributed commitment? Well, for this we would like to have at least one honest dealer that shares to a fully honest set of recipients. Sorry, not recipients, to the parties PI. And additionally, we would like to ensure that all adversarial RIs must be committed before reconstruction. Well, in the distributed commitment protocol, what we need is we need at least one honest party in each set. And how to obtain this? Well, the idea would be to use T+1 dealers. So this will ensure that at least one of the parties is honest. And have each dealer shared towards every t+1 size subset of a set of a size 2t+1. Since we are sharing to the subsets of size t+1, this ensures that the second property is satisfied. So at least one of the parties in each of such subsets is honest. And additionally, since we are using this set of size 2t+1, this means that there are at most t parties that are dishonest. And so there are t+1 parties that are honest. And so there will be at least one honest subset that is being used by each of the honest recipients, each of the honest dealers. OK, so this is pretty neat. And what it gives us a protocol for partial randomness generation with the following resilience. So we will be able to have protocol which has 4 t+1 parties in the descending leaks model. And in the execution leaks model, we can save a little bit, specifically in the reconstruction phase, and obtain 3 t+1 parties. OK, so I cheated a little bit because I said that we are interested in efficient protocols. This one actually has also, same as the unconditional one, exponential computation. And this is not the case for the other protocols in our work, but I just, first of all, like this one. And second of all, the interesting part about this one is that, as we will see in a few minutes, it comes pretty close to achieving optimal resiliency. OK, and so this is the last part of the talk. So very briefly, I would like to talk to you about the lower bounds that we obtained for the partial randomness generation. So we would like to know how many parties do we actually need. And let's start with a simple example. Let's say that we have 3 parties. One of them is corrupt. If you think about it, you can consider the very last party. So like, let's say if we think about the party P3. This party can do like lots of things, right? It can compute its message M3 that will be generated by using messages M1, M2, and also the private messages that this party received, along with like any randomness that this party has, obviously. This party can also simply not publish anything, and so there are like a lot of things that it can do. However, if you think about it, well, either the 2 honest executions of P3 lead to different coins with non-negligible probability, in which case what a dishonest P3 could do, it could simply bias, right? Because it could simply compute the outcome in its head. And then if it's happy with the outcome, it can, for example, just publish it. Otherwise, it can just not publish anything. So in this case, this is not good. P3 can bias. And else, I mean, this is very informal, but like else, P3's contribution in a sense doesn't really matter. So the coin is determined by the public values of P1 and P2, except with some negligible probability. And what it means is that it means that now actually P2 can also predict the coin, in the sense that we can set P3's public values to be bought. And if P1 and P2 behave honestly, then the value can be computed even without P3's contribution. And so we now can repeat the same argument for P2. So either the 2 executions can lead to different coins. And the important part is that P2 can actually predict the outcome in its head, in which case P2 can bias. Or the coin is determined by P1. And I mean, as we have one correction, this is clearly not secure. So P1 can bias. Can we generalize? Well, in the sending leaks model, where the adversary receives the value upon it being sent to a corrupt recipient, the answer is yes. And the argument is fairly simple, so we can apply the same argument to blocks of size t instead of parties of size 1. However, in the execution leaks model, the situation is actually more interesting. So here, the adversary will receive value upon the execution of a corrupt recipient. And the problem is, like, if you try to apply the same proof idea, it actually is not clear whether you can get the same result. Because maybe the set of P2 can bias, but maybe only if it knows all messages to everyone in P2. And the problem is that maybe the first party in this block will already have to like commit itself to some public message, right? But like at this point, it doesn't know the messages has been sent to the next adversarial party, because this next adversarial party will only get it like once it is being executed. So yeah, this is not clear. And we use some tailored technique to prove impossibility for a specific case of t equals 2 and n equals 6. Which is also a, I think, very interesting proof. And it would be super interesting to see if we could generalize this. Okay, so this is just an overview of the results that we have. So the top line is the unconditional protocol by Nielsen, Ribeiro, and Abramsky. Then we have a protocol based on the DDH assumption that is by the same set of authors as this work that was published at FC 2024. And then in this work, we have sort of a suite of different protocols with, as you can see, different resiliency and also different assumptions and different communication and computation complexity. So the one that I introduced is the non-attractive commitments one. So for sending leaks, it requires 40 parties, but unfortunately, it is only efficient for t in O of log lambda. And in the execution leaks, we know that it requires 3t plus 1 parties. And achieving t equals 1 and n equals 3 is impossible. Same for t equals 2 and n equals 6. Yeah, this is pretty much all that I have. So there are a lot of interesting questions. For example, it would be interesting to further optimize roll complexity since there are still some gaps between the lower bounds and our constructions. Also, it would be interesting to optimize communication computation and also obtain maybe different primitives, so not only randomness generation. Yeah, that's all I have. Thank you so much.
Thanks, Lisa, for the wonderful talk. Do we have any questions? Yeah, I have one, Lisa. You were mentioning that this is optimal resilience in your protocol. Is it, I mean, where do you prove the optimality?
Well, I mean, it comes close, right? So like for the execution leaks, for example, we have the 3t plus 1, right? This is our protocol. And we know that t equals 1 and n equals 3 is impossible, right? And like t equals 2 and n equals 6 is impossible. So for this one, for the execution leaks, we do not really know if you could generalize this, right? And for the other one, yeah, we know that less than 3t plus 1 is impossible, and the protocol that we have is currently 4t.
Thank you. Thank you very much. If there are no more questions, then let's thank Lisa once again for the wonderful talk.
Thank you.
Okay. So the second talk of this session is by Divya Ravi, who is an assistant professor at University of Amsterdam, Netherlands, and she will be talking about separating broadcast from cheater identification. Thank you.
Thank you. Hello, everyone. So yes, this talk is about separating broadcast from cheater identification, and it's based on these two works. The first one is with Yash, and it's already on the archive, and the second one is a sort of a follow-up, again with Yash, and also Yure and Sofia, who are all here today, so I'm happy and excited to be presenting. Okay, so let me begin with what MPC with abort means. So it's basically a kind of security in which it may happen that corrupt parties get the output while honest parties do not, but this can again be of different flavors. So there is a flavor, the weakest one, which is selective abort, in which the corrupt party can actually select which of the honest parties can get the output. So in this case, maybe the adversary has selected that only the third party is getting the output and not the fourth one. A stronger notion is that of unanimous abort, in which the honest parties are in agreement. So either they all get the output or they all output bot. But both the selective and unanimous abort are sort of dissatisfying in some way, because imagine that as an honest person, you are participating in the protocol, and at the end you got nothing. So it's like a denial of service attack. So a more preferred notion is that of identifiable abort. And in this case, also it can happen that the honest parties did not end up getting the output, but at least they identify one of the corrupt parties. So it's still progress in some way, because maybe they can remove this cheater and still proceed. So it's still some incentive. And more recently, we introduced this notion, which is a sort of a hybrid between the selective and the identifiable abort, and we called it as selective identifiable abort, or SIA. And this notion is sort of similar to selective abort in the sense that it can happen that some honest parties are getting the output and some are not, but it has the added advantage that the ones who are not getting the output, they will be able to locally detect a cheater. Okay? So it's not, unlike the IA case, where everyone identifies, all the honest parties are in agreement and they would identify the cheater, here maybe only some of them are locally identifying the cheater. Okay? So this is how the implications follow, because agreement is a stronger property to demand, and that's why UA implies SA, and SIM for similar reason. And the identifiable counterparts are obviously stronger than the ones without identifiability. Okay? So what I want to focus on is the selective identifiability for this talk. And this was a notion we introduced with Ivan, Sofia, and Luisa just last year, like a couple of years ago. So like I mentioned, it can happen that some honest parties get the output and some others locally detect a cheater. In fact, if you have multiple honest parties who did not get the output, it can also happen that they're detecting different cheaters. So you don't have agreement also in terms of the cheater that you identify, not just in terms of the output, whether you're getting it or not. And more recently, with Yash, we sort of had a provability dimension added to it, and this is what we call as provable identifiable selective abort, or PISA in short. And here, in this case, what happens is that these parties, which locally identified the cheater, now not only did they locally identify it, but now they get some sort of a proof of cheating certificate that they can show to any external person and basically implicate the corrupt person. So in this case, for example, this fourth party, he can prove that P1 cheated, and the other one can prove that P2 cheated to anyone maybe who asks him that why you did not continue the computation or something like that. So these are the two relatively new notions, but now the question is that there was already so many notions, and we were kind of happy with this notion of identifiable abort, where you identified the cheater and you were in agreement. So why are we complicating our lives and introducing these new notions? And there is a very good reason for that. Thank you. So I hope that got your attention, if not whatever I've been saying so far. This is the exact reason that we don't really talk about broadcast, and all these IA protocols are actually using broadcast. And this is an expensive resource to use, but these IA protocols sort of have to use them because it's known that broadcast is necessary for identifiable abort. So this is a cost that they have to incur. But somehow, because there's a lot of literature on trying to make IA protocols more efficient, but the broadcast costs are sort of swept under the rug because, of course, they are comparing with previous IA protocols, which are also using broadcast. So it's not making a difference in their efficiency gain. So our sort of reason for why we want to introduce this notion of PISA and selective identifiability is that these can actually be achieved without broadcast. So maybe if selective identifiability is something also with provability, that is something that is good enough for your application, you could consider using that and hope for more efficiency gains than the regular IA notion. Okay? So now the remaining part is just going to be about PISA and PC, so I want to make sure that you understand it. So basically, it's a guarantee in which at the end of the protocol, each honest party either gets the output or it has a proof of cheating certificate against a corrupt party. That's what the notion of PISA is. And the goal is that we want to design simple and efficient protocols having this particular guarantee. Now, maybe some of you are thinking that if an honest person locally detected somebody and can prove it to anybody external, why doesn't he just send it to the other honest people so that now they can also be in agreement about who the cheater is? That's a totally valid question. But now, in order to be in agreement with the other people about who the cheater is, you will need to broadcast this proof of cheating certificate. And that's what we were sort of trying to avoid. But technically, it's still possible that if you want to, say, like use broadcast only once, then you could, for example, design a PISA-MPC protocol and then just add one round of broadcast in the end to do this broadcast of proof of cheating certificate, and then you can go back to your notion of IA if you like that more. So it's still a way to get IA with just one round of broadcast. Okay? So I want to highlight some of our important results. So the first is that we showed that honest majority is actually necessary for this notion of PISA-MPC. Now notice that this is different than the case of IA, which was possible also in dishonest majority. But now some of you may think that if you have an honest majority, then why don't we just go for the very strongest notion, that is of guaranteed output delivery, or GOD. But again, the reason is that GOD would need broadcast, while PISA can be realized only over point-to-point channels. And plus, there could be some situations where maybe it's more preferable to identify who the corrupt person is than getting the output. For example, there are a lot of GOD protocols in which they don't identify the cheaters in any intermediate stage. Maybe they only identify conflict pairs, and then the adversary could drag out the protocol a lot by exposing like one conflict pair at a time, and maybe you are taking many more rounds, or it's more resource intensive. So for your application, if it makes sense to abort early with identifying somebody rather than taking this resource intensive sort of worst case path, then it could make more sense to go for such a notion. Sorry, I think. Yeah, and the other example was, I think, where you have an MPC protocol run among the nodes owned by the same entity. So maybe then it's more important to locally identify where the problem is rather than always getting the output. Okay? The next result that we have is that there is a sort of a general compiler that begins with any IA MPC protocol that uses broadcast and transforms it into a PISA protocol using only point-to-point channel. And this is in the honest majority, because honest majority is necessary, as we showed. And lastly, we showed that 3 rounds are sort of optimal for this notion of PISA-MPC. So for the rest of the talk, I want to sort of give the ideas of these behind these 2 results. So beginning with the compiler, but before that, I want to present this building block that we used in the compiler, which is a very simple and effective building block. So it's basically a PISA variant of this broadcast functionality. So remember, what was PISA? It was about either you get the output or you have a proof of cheating certificate. Now, if I want to project it just for the broadcast functionality, the way we define this variant is that at the end of this protocol, the honest parties are either getting a signed message from the dealer or they have a proof of cheating against the dealer. So it's a more specialized case in which the proof of cheating would be against the dealer for this specific broadcast functionality. And this is something that requires an honest majority that we showed, and it can be realized just over 2 rounds over point-to-point channel. And this is a very simple and effective protocol which was sort of built on the Echo broadcast protocol of Goldwasser-Lindell, for those of you who are familiar with it. So I will just maybe quickly explain it for the case of 5-party and 2 corruption, but it generalizes for any honest majority. So the first round is, as you might have expected, that the dealer is signing the message and sending it to everyone. And the second round is that parties are just echoing these messages. So if you got a valid signed message, then you send it to other people. If you did not get it, then you sign on a message saying bought, which is sort of that you're complaining that you got nothing valid from the dealer, and then you exchange it with your co-participants. And now the most interesting part is how we compute the output of this. So first you check if you are able to get any potential cheating certificates. So for example, if you got 2 different messages, both with a valid signature by the dealer, that's something that you can use to implicate the dealer, because you know that an honest dealer would never sign on 2 different messages. So this would be a proof of cheating against the corrupt dealer. Another thing that you might look for is you can check if T+1 people are basically signing on bot, meaning that they are complaining that they got nothing from the dealer. In this case, T was 2. So what this means is that at least one honest party complained that they got nothing from the dealer, and this could be enough to prove that the dealer was cheating. Now, if you were not in any of those 2 cases, then we are sure that you must have got a unique signed version of the message, then you just output that. So this two-round subprotocol has this property that at the end, you either have a signed message from the dealer or you have a proof of cheating against the dealer. Now this is the building block that we will be using in our compiler. So this compiler basically begins with this identifiable abort protocol, say pi, and it uses broadcast channels. And what we want to get to is, we want to get to this PISA MPC protocol pi prime that uses only point-to-point channel. So the first step is, of course, we want to get rid of those broadcasts. So what we do is we simply replace those broadcasts with this variant of PISA that we just saw, which we know that we can get using 2 peer-to-peer rounds. So you just replace them. And now there can be various possibilities. So it can happen that, just think of one instance of this BC-PISA protocol. So maybe it could happen that it failed in the sense that everyone did not get the intended message, and there was at least one honest party who did not get the intended message, but by the property of PISA, it must have got a proof of cheating against this dealer, right? So say that we are in that case. Now what this party can do is he can simply forward this proof of cheating certificate to the other people in the subsequent round, and then he can just output this proof of cheating. And this is a valid PISA output, because what this needs is either the function output or a proof of cheating against a corrupt person. And in this situation, we got a proof of cheating against the dealer of this particular instance who failed. So this would be a valid PISA output. Now next, let's look at the other case. Say that nothing failed, all those broadcast PISA protocols succeeded, meaning that everyone got everything that they were supposed to get, even in the original protocol. All the broadcasts were perfectly emulated. So now they can just continue to compute the output of pi like they did in the original protocol. So they can just continue to do that. And then now in this, again, there are two possibilities, because the IA protocol could either be successful, meaning that the honest parties all got the output, in which case that's again the function output, which you could just output as the output of the PISA protocol. Or in the other case, if the IA protocol fails, then by the property of IA, you know that all the honest parties would have agreed on a common cheater, okay? So it could also happen that the output of the IA protocol was basically an abort identifying PC as the common cheater. But this is not yet a valid PISA output, because this is not something you can use to convince an external person. So now but you have the property that, because of the agreement of the IA, you have the property that all honest people, and there are at least T+1 of them, they have all identified the same cheater. So now what you can do is, they can initiate an instance of this BC-PISA protocol to send this message that I have identified PC as the cheater. And if you are able to aggregate T+1 people saying that they have identified the same person, PC, as a cheater, then that's something that you can use to convince an external person. So this would be a valid proof of cheating against this party PC, and that's again a valid PISA output, okay? So this is basically roughly the sketch of our compiler, in which you begin with this IA MPC protocol using broadcast, and you end up with a PISA protocol using only point-to-point channel, okay? So now I want to move on to explain our round complexity results. So we showed that 3 rounds are actually necessary for this notion of PISA MPC, and the proof is by contradiction. So assume that it was possible, there was in fact a 2-round PISA MPC protocol, say pi, which was computing this particular function. And the function is basically the first party has a single bit, and the second and third party have M0 and M1 as input, and the output is nothing but just the first party is getting MB, and the others don't have any output. So say that by contradiction, there was a 2-round protocol which was having the PISA guarantee and able to compute this function securely. So now any such protocol will look like this. Remember that it's only over point-to-point channel. So it will look like this, where these parties are talking to each other over the point-to-point channel. In fact, since this is a special kind of function where only P1 is getting the output, we can, even without loss of generality, say that the second round only has messages towards P1, because the other parties are not really getting the output, so there's no point in them receiving messages in the last round. Okay? So this communication pattern is sort of without loss of generality for this function. So now let's think of a scenario in which, say, execution E1, where this P3 was corrupt, and the input of the honest P1 was the bit B equal to 0. So now what this corrupt P3 did is that she was honest in the first round, but in the second round, she simply dropped her point-to-point message to P1. Okay? So now P1 is an honest person who should get the output of PISA according to the guarantees. Now that means that she should get either the function output, which would be M0 in this case, or she should get a proof of cheating certificate against P3. But now, how can she ever prove that P3 did not send her anything over the point-to-point channel? And if it was possible for her that this misbehavior led to a valid proof of cheating, then that would be problematic. Because think of another situation in which P1 was actually bad and P3 was good. And in that one, the bad P1 can always just say that I got nothing over the point-to-point channel in the last round. And you cannot think of that as a valid certificate. You can't afford implicating the honest P3 in that case. So this kind of misbehavior is not something that you can produce a valid certificate for. So that's why that option is ruled out. And the only option is that in this situation, P1 should be able to output M0. Okay? Now we sort of look at another scenario, which is a symmetric case in which P2 is this time corrupt, and the input bit of P1 is 1. And it's the same kind of symmetric situation in which P2 is honest in the first round, and in the second round, she's dropping her point-to-point message to P1. Now, again, for the same reason, it's not possible for P1 to get a proof of cheating certificate against P2 because P2's only misbehavior was not talking in the last round, and that's not something that you can prove. So that's why in this situation, again, P1 should get the function output, and in this case, the function output is M1. Now we move to the final scenario in which P1 is actually corrupt, and she starts misbehaving in the first round itself. So what she does is that towards P2, she behaves with respect to input 0, and with P3, she behaves with respect to input 1. And then in the second round, anyway, she's not saying anything. She just waits to receive messages from the others. So now at the end of this scenario 3, what she can do is that in her head, she can think of the situation in which P3 had never sent her a round 2 message. Okay? So it's basically just dropping a message from the view, right? So it's something that she can always imagine in her head, that what if P3 had never sent me a message? And why is she doing that? Because she wants to sort of create the same view that honest P1 has in the first situation. Because it's sort of the same, because P1 talked with input B equal to 0 to P2 and got a message just from P2 in the second round. And the same thing is sort of happening here if she ignores the messages from P3. So this means that basically the view of P1 here subsumes the view of P1 there. And since honest P1 could compute output M0 in that case, that's why she should be able to compute M0 also here. Okay? And now she can do this symmetric strategy in her head again, in which now she imagines that what if P2 had never sent me a message? Then her view sort of becomes similar to the view of honest P1 in the second situation. And since that was enough to compute output M1, it means that this corrupt P1 in scenario 3 is able to get output M1 as well. So this is a contradiction because as per the ideal functionality, the corrupt P1 should never get both M0 and M1. So we have arrived at a contradiction which shows that 2 rounds were not enough and in fact 3 rounds are necessary. Okay? And in the last few minutes maybe, I'll just talk about the upper bound. So for the matching upper bound of 3 rounds, what we did is we took one of the 2-round IA protocols from a previous work, and in that one, we were using broadcast only in the second round. So what we can do is we can simply replace that second round of broadcast with this BC PISA variant that I showed you. So if you replace that, and since we know that that can be realized using 2 points of peer-to-peer, this will overall give you a 3-round protocol over point-to-point channel, which is achieving PISA. And we had to make some minor modifications with respect to the setup of the original protocol, but this is essentially the main idea. So just to summarize, this PISA MPC is a new notion which basically the main advantage is that you can avoid broadcast and you have this certifiability property. So it's something that you can consider, and it does have a lot of promise to lead to much better efficiency than the regular IA protocols, which in the paper we also demonstrated for the case of ECDSA. And I request you to look at the papers in case you're interested. And we looked at the general compiler from IA to PISA, and then the round complexity result. So that's all. Thank you.
Thank you, Divya, for the wonderful talk. Are there any questions? Yes, please.
And thanks for the great talk. So I saw all the 4 abort properties. It was a very good graphic. So I had one question.
Yeah.
Say multiple parties behave in a faulty manner, right?
Yeah.
Do you have any abort guarantee that identifies all of the faulty parties that were responsible for the protocol failing?
I mean, that's a really good question. So, I mean, also with my quota, at some point we were thinking about it. So, I think some protocols like GMW have that property that every misbehavior is caught. And we were sort of, like, it's like a complete identifiability sort of property that no misbehavior gets undetected. But I don't know if it has ever been, like, formalized as a property. So I know that some protocols satisfy it. But yeah, I don't think it's a general thing for IA protocols. In general, they just ask to identify one corrupt cheater at least.
Okay.
Yeah.
I had also one small follow-up question.
Yeah, yeah.
Since you're talking about broadcast,
Yeah.
there have been works that sort of work with the quorum intersection argument in synchrony. Like if you say get 3n by 4 votes out of, you can be sure that there has not been any other equivocating proposal that has been in circulation or something. Have you considered arguments like that while considering an abort procedure like that, like this?
So I'm not exactly sure, but I know some, you mean like there's enough overlap between two sets of people. So I have seen more of those things in starting from 3t+1 onwards. I have not really seen such things in 2t+1. So since we are in 2t+1, I mean, we did not use such a technique, but maybe, yeah.
Yeah, it's a small series of works called Thunderella in the blockchain literature.
I see, but I would be interested to hear about it, maybe if there's some, if it's of a similar flavor. Thank you.
Thanks.
Thank you for the nice talk. I was curious about the exact definition of the auditor. So he gets the, does he get the entire like state of the party or just the output?
He just gets the certificate, like the proof of cheating certificate. Like in the example of, for example, the broadcast protocol that I showed you, he will just get those 2 signatures on different messages, or he will get like t+1 signed messages by people saying bot. That's all that the auditor will see. But we also assume that he knows who participated and things like that. And then that's all he has to verify. He doesn't need, that's also a big advantage, that he doesn't need the transcript or, the entire state of an individual.
But does anything change if, say, you give the auditor like say partial transcript, like say like the last round of interaction? Like maybe, like my intuition was that maybe if you get like the last round of interaction, like basically the transcript of the last round plus the output of each party.
Yes.
Then maybe you could do this like with information theoretic security, where like in the last round you have some kind of grades and then you just get the set of grades that each party received.
I see. No, it's a good question, but we also wanted to sort of have that the auditor, it's enough for the auditor to just talk to one person. It's not necessary for him to talk to sort of everyone. So, for example, if he just talks to me and I have aborted, then in these type of situations, I can give you the signatures. But if I give you my version of the transcript, then the auditor cannot believe me, right? So he needs inputs from other people also. So this is more like just auditor talking to one person, But maybe if we allow him to talk to multiple people, maybe, we can think of if something stronger can be obtained. Yeah.
Thank you.
Hello.
Yeah, Divya, this side.
Okay. Sorry.
Thanks a lot for a wonderful talk. Can PISA MPC can be applied for a secured statistically MPC of a biased coin using blockchain as such?
So first of all, we're in computational security because PKI is something that we are assuming. We are always assuming digital signatures. So I don't think, I don't know about particularly about biased coin in general, but this does not scale to statistical security.
Okay, statistical.
Yeah.
So if there are no more.
Interesting. So I have here with me Rajiv Raghunath, who did his PhD at IIT Bombay, now is a postdoc at IIT Madras. And I'll tell you about some work we did together, and we are continuing to do together, along with a few other people at Trust Lab. And that is this programming language for MPC. So first thing is, I think MPC needs a programming language, or you could ask, does it need? And here's the answer. The idea is that we write a lot of protocols in our papers. They're usually imprecise, a lot of details are missing, and then someone tries to implement them. That may not be what the authors had in mind. So it'd be great if cryptographers could themselves write protocols as formally as possible with minimal extraneous syntax. We don't want to probably write a full-fledged program which implements your protocol. So that's one thing. The other thing is there are a lot of idioms that as cryptographers, as MPC researchers, we use that are not immediately there in a programming language if you were to use, I don't know, Python or C++ or something to implement your thing. And some of these idioms are, so we have a notion of schemes like BGW, GMW, YAO, whatnot, speeds, which are used to take a functionality and transform it into a protocol. So that's one of the most obvious things any programming framework for MPC should support, and many things out there already do that. But there are also things, as somebody writing protocols, we often use protocol composition, so invoking subprotocols, right? Or MPC in the head. A lot of protocols in the literature use MPC in the head, but it's easier said than done to implement that in practice. If you already have an MPC that has been written as a two-party protocol, say, and you want to run it in the head in another protocol, taking that program and transforming it into a new protocol is not easy in an implementation. So we'd like to support all of those things natively. That's one thing we do. And the other thing is, of course, it's not just, even though we intend it mainly as a specification language, at the end, you should be able to just take that specification and compile it and run it with no extra effort. So that's a goal. So, there's a separation of two kinds of things you would like to do if you want to implement an MPC protocol in real life. So cryptographers can focus on what we do better, namely write the cryptographic protocol, right? So for that, we'll use a high-level syntax, not a low-level programming language. And we'd also like to use a lot of standard protocols, oblivious transfer or whatever, right? And also transformations, MPC in the head kind of things. And finally, we have all these protocols that people are still working on because there are a lot of scenarios for which you need to develop new protocols. And as and when they come, if you want to actually compare their performance, it's very hard if you want to compare practical implementation performance, because if different sets of implementations are there, they are, you're comparing apples to oranges. A lot of the efficiency might be because of low-level implementation details and not the protocol's inherent efficiency. So if you have a common platform where all these protocols are written in high-level syntax, it's a more apples-to-apples comparison. And last but not the least, a programming language is a great pedagogical tool to kind of show, here's what a protocol looks like with all the details filled in. Okay? Now, while cryptographers do all that, there's a lot of other work that's needed to make an implementation efficient, and we should get professional support for that, I guess, and rather than pretending to be compilers, researchers. we should actually get compiler folks to optimize low-level implementation details, communication, concurrency issues, memory management, data formats, a lot of things. And also, implementations out there today probably, it's not very easy to handle things like, say, side channel attacks and issues like identity management or debugging tools. Of course, there are various implementations. Each one does its own things. Here, the idea is that the programming language comes with a toolkit with, the platform will come with all these things. At least that's a vision. Right now, we are not there yet. Okay, so let me tell you about what this new language looks like. And what I'm going to do is a bit of time, so run through a bit of the syntax, show you some examples, and hopefully get you excited about it. Okay, so this is just the history. Started several years back. Some people, Divya and Nishant, they're all here from MSR. We started discussing this way back in 2017, but we are still not at a place where we can release it. We're very close to it, hopefully. So soon, we hope to release it as an open standard and open source, that's open standard language with an open source reference implementation. Currently, you could say what we have is an alpha version. If you are interested in alpha testing, please let me know. We will be happy to share the code and documentation. But we are hoping that in the next few months or so, we should have a public release. Of course, I should acknowledge that there is a large body of MPC implementation work already out there. MPC is orthogonal to those things in many ways. So it's not about actually just deploying a particular MPC, like say speeds or particular protocol. It's a protocol specification language to describe new protocols then, right? If you write your new crypto paper, you could hopefully translate that into a program without too much effort. Maybe you can get a student intern or somebody to do that. Yeah, so you can prototype new schemes and it can coexist with other implementations. That's a vision that the MPC protocols can use sub-protocols. So by MPC, I mean program. So by the capital C is like, it's a C-like language for MPC. That's a MPC. Okay, so let me just give you this little, view of what the syntax looks like. So I'll start with a little example. So two parties, A and B, they just want to exchange data. What would it look like? So this is what we'd like them to do. A gets an input from its environment, right, and stores it in a variable X, sends it to B. B stores that in its variable Y, and then outputs it to its environment. And I'm going to have the same backwards also from B to A. So here's what the syntax essentially looks like. You would want to say, okay, inside A, there has to be these variables X and Y. It should read, so this is our way of saying read from or send to, read this variable X from the environment. Environment is a keyword, environ is a keyword. So you read it from your environment. And same thing happens in B. And now A and B exchange. So this is a code which essentially says A's variable X will be sent to B and will be copied to Y. Okay? So this all, as a cryptographer, you will need to write. Of course, internally that creates a communication from A to B. But here it's as if you assign one variable to another. And here from B, you copy X to A's Y. And after that, A and B can locally output their inputs, the variable Y, to the environment. So the actual code looks pretty much like this. These little pieces will show up inside a protocol block. So instead of functions in C, we have protocols. And in the protocol, you declare which are the roles. So here's a protocol with two parties, A and B. And in A, you do these things. In B, you do these things. And then there's some public code. So it's not in A or in B. It is between A and B. We write it outside of these blocks. And then again, in A and in B, you do something. Okay? And you have all the nice things like, you don't need to put braces if it's a single statement, otherwise you put braces to get a block. So C-like syntax. The way I've written, so this is one way to do communication using this syntax. It's nice in that it won't accidentally create deadlocks. If A sends something but B is not ready to read it, in your protocol, if you specify it that way, it will be a deadlock, right? Or B tries to read and A is not sending. So this avoids that. On the other hand, this is a little slow. Maybe you want A and B to start sending simultaneously, right? So the syntax allows for that also. You can say this. In A, you send X to B, and simultaneously in B, you send X to A. So, these are now local actions. They're not synchronized, and it's up to the programmer not to create deadlocks. Of course, in future, you could try to detect some of these, common errors. We don't do any of that right now. But the syntax allows this if you want things to be. And in this case, this is what the entire protocol looks like. Okay? So this is a real protocol. It compiles, it runs, it'll do what you need to do. But this protocol is not, you might see that, I have two parties here. They're doing a lot of same things. I've duplicated the code here, maybe not what you want to do. Often you have many parties and you have an instruction saying all of them should do the same thing. Well, we can support that. So you can have a notion of a party array. So here we say there's an array of parties, two parties in this case. So they're called P0 and P1, and they are doing the same thing. So that same thing shows up in the code here. We have our own little nifty syntax for doing some of the common things we need to do. So we want to say each party will do something. We can write this. This full-fledged syntax. You can say in each P hash I. Hash I is, it implicitly declares a counter that goes over the entire array. So this is some of the little things we have added, not quite there in C. And yeah, here you send X to 1 minus I, P1 minus I, you read Y from P1 minus Y and output it. So same thing as what happened in the previous protocol. And this is also the way to write protocols with variable number of parties, right? So you can have that, instead of 2, it can be a variable n, which can be declared here, by the way. The variable is a parameter to the protocol. In this silly example, you could say silly, all you're doing is reading something from the environment and sending it to the other party. Maybe you don't need to store it anywhere. We have syntax to let you say things like forward, one message from here to there. It kind of loses which type of object it is. But if you don't care about that, this is more convenient often, just to say, send something from here, read something from environment, one variable from environment, and send it to the other party, and vice versa. Okay, so this does the equivalent thing. In fact, this does, if you, instead of just sending one thing and you want to keep sending many, many things, you don't need to write a loop. We allow you to write connect a port. So connect this port to this port, right? So everything that coming in your environment will go to the other party. So this essentially is a forwarding forever. And finally, you can, you're connecting both ways. It's a duplex channel. This entire thing is, this is the entire protocol for achieving this whole thing. It's a single line saying connect this port and that port, means it's going both ways. Okay? So just to say that, some of the syntax has been designed so that common things can be done in a very terse manner. How do you take a protocol and run it? So first you have to write a protocol in MPC, in our language. Then there's a little tool we have called MPCC. So that's a compiler. What currently our compiler does, or rather, the compiler will produce binaries. What currently our compiler does is internally it will produce C++ programs, which are then compiled. But at the end of the day, you get binaries, one per protocol per party. Per party, as in if it's a party array, you'll just get one program, which takes a party index as an input while being executed. To run it, you also need to prepare a little configuration file. You will say that this is the IP address of the other party and so forth, and this is the protocol I want to run, and so forth. And we have a little tool called MPCR, which you use to run the protocol. And as this is running, it will load binaries as needed for various parties in the protocol and its subprotocols and so forth, and produces output. Currently, the output comes either on the console, or we can produce output in a file. In future, we'd also like an API so that these protocols can be invoked from other programs, written in other programming languages, right? We don't have that right now. Just one quick example, one more quick example. So there's a protocol, again, kind of a silly protocol. You could say there's a trusted party, T, that takes inputs from a bunch of parties, P0 up to Pn minus 1, who themselves get their input from their environment, sends it to this party T, who sums it, and sends the sums back to every party, okay, who produce their local outputs. Let's see what the code looks like. I just want to show a few other things in the syntax here. First of all, this summation is happening in some field. You can pass the field to this protocol. You don't have to bake in the field into the protocol. Instead, the protocol takes that field type as a parameter. It's also taking this n, which is the number of parties, as a parameter, right? So you can write one protocol that works for any summation of any number of elements over any field. Of course, the field data type is something we have built. This is what the protocol is, what the parties are doing. They're just reading something from the environment, passing it on to this party T. You could have done it using a forward also here. And then the party, and then it's reading the sum from the party T, because T is what T is doing. It is going over a loop, summing up, accumulating everything, and then sending that sum to the parties. This is the entire program, that does that. Yeah, so when you're using a type, a custom type, you need to declare it somewhere and also implement it in the backend, which we have done. It can come with interesting custom functions, right? You want to sample random elements from the field. You might want to do Shamir secret sharing out of field and things like that. You can be supported as custom functions in the field. Yeah, so user-defined data types. If you want to define your own data types, you don't need to change the programming language. There's a way to, you can write a class, C++ class for the data type and put it in the backend. And the reason for this, instead of baking all these data types into the programming language, is that you might want to use your own efficient libraries for, say field arithmetic or PRF evaluation. So you define your data type for that, implement it in whatever you want, and then it can be combined with the libraries we have. Okay, so continuing with, I have 10 more minutes, so I'll show you a few more things until I run out of time. So here's how you start a subprotocol. Okay, so here's a top-level protocol which has two parties, and when that protocol session starts off, this is a snapshot of that scenario. The party A is running, party B is running, maybe in a different computer. We'll talk about that in a bit. And they have these ports. A is connected to its environment, and so that's the port, environ port, and similarly B has its environ port. Also, A has a port called B that it uses to talk to B. B has a port called A that it uses to talk to A. And now suppose they want to start a subprotocol. Okay, the subprotocol is called bot. I'm not, I just declared it here. There's a way to kind of this for our compiler to see what kind of a bot, what kind of subprotocol it is. That protocol may not be defined in this file, right? So there's a declaration here saying, okay, there's a protocol called bot, which has two parties called P and Q, two roles called P and Q. Okay, you're planning to start sessions of that protocol. So I have declared a bot session, and the session variable is called child. And here is how you'll create that session. You'll say open child, open the session called child, and P at A, Q at B. So this protocol, this is inside this block, inside this protocol that A and B are running, right? So we are saying A and B are parties in the top protocol. They are starting a bottom protocol, a child protocol, and P will be hosted at A and Q will be hosted at B. You need to specify that, right? Like you're calling an OT, who wants to be the sender, who wants to be the receiver, things like that. This currently it's a simple statement there. It can be a whole logic there, how you decide who is hosted where. You can write standard. So, by the way, we have all sorts of if, then, if, else, and for loops, and so you can use that syntax here. Okay, when you open this, A gets a new port called child.p because it has a session child and it's hosting P. If there are more parties that are hosting, it'll get one port for each of those parties, and B gets child.q, and now it can use those ports. And P's environment is A, and Q's environment is B, right? And you can say things like, okay, in A, send something, I'm not defined here. Suppose there is some variable called input to the sub protocol. Send that to child.p. So it'll be written here. P can read it from its environment. And then when P writes something into its environment, A can read it like this. You can read the output from the child. B could also do, it could do here, what it's doing is it's connecting its environment and P, so whatever B writes here goes out here. Okay? Who knows, maybe that's what you wanted. So that's syntax for starting a session. The big picture looks like this when the execution model. So instead of, in a programming language like C, you have a stack of function instances, frames. We have not functions, we have protocols, or rather more precisely parties in protocols. So what happens when you start off, there's a root session that's created. MPC protocol could be running between multiple locations. Each location starts off its own little MPC engine with a configuration file which says, I'm hosting a particular party in the root protocol, some protocol that we are interested in. So in each location, you would have one party hosted, if you're running it honestly. And these parties can then, in this root session, root protocol, you can start other protocols. Right? So maybe you open a child session. And as we mentioned, they get their environments to the root protocol. Then in turn, inside this protocol, you can open child sessions, right? So it's like a stack. Instead of having a stack, now you have this tree. It's a tree because it doesn't have to be just, you can have multiple, you can make calls to multiple sub-protocols and they can exist concurrently. It's not like this has to finish before you can call another sub-protocol. So everything runs concurrently here. Another thing is when you open a session, it's not like it has to be between these two locations. You could, for instance, have one party here hosting any number of roles in a subprotocol. So it could all be hosted by one party. So this is the kind of thing you would do if you want to do MPC in the head. You can have multiple parties of a protocol running in your head. So that brings me to protocol transformations. There are two kinds of transformations, white box transformations and black box transformations that we support. White box is what I talked about in the beginning one example of that would be applying a scheme to a functionality. Okay, so here in general you're taking the code of an MPC protocol written in MPC language, producing another MPC language protocol. And I'll illustrate this in a bit, how to implement. But apart from this, there are other transformations we do. We support like flatten, so you can inline sub-protocols because starting a subprotocol comes with some overhead, so sometimes you might want to avoid that. So you can flatten it. Certain other things like isolate merge. These are useful actually in a supporting role for MPC in the head. Black box transformations is MPC in the head. So this means you're not looking inside the code, you're running the code of a protocol, of a party in a protocol as a black box. And yeah, I'll come back to that. So let me just go back to white box protocol transformations, give one example. So here is our earlier protocol, the SUM protocol with a trusted party. Now you don't really want a trusted party in MPC. You would like to replace it. Suppose you have written a scheme which can take a trusted party which does linear operations, and you would like to write a scheme, right? That does some secret sharing and among a bunch of parties. So here is what a scheme would look like. So you would be saying, okay, my scheme is called something, linear MPC, and it has a bunch of parties, n servers. And there's another party T that I'm planning to replace. Okay, so my scheme is written as I'm planning to replace this party T with n servers. I can have any number of parties here, but only one party here in our current syntax. And what is written here are the templates. It says, okay, if you see, so this kind of code, in some party Q, if you're sending a message to T, well, T is going to go, so we need to replace that with some other code. So here, there is a match. It said in some party P, send X to T. So here, this matches. There's a party Q in here, sending some variable which is of the field type, variable in Z, in Q, is being sent to T. So this template would match this here. And what will we do? We'll replace this code with this code. So in P, instead of doing this, now it'll do something else. I've skipped it. It'll be like, you secret share it to all the server parties. Secret share your Z. And later, let's say here, this part in T, the part T is reading something from a party PI, right? From some party Q, which is PI here, T is reading some message, some field element, okay? And here is the little code you should replace it with. So now no more T available, but there are these server parties. Each of those server parties, this is a convenient way to do this. They will have a variable also called whatever is this variable, right? So here is a variable temp in T. Each of those servers will also have a variable temp, in this case Z. And you read something from the server, it will be a share from the party PI to this variable. So this is how you would write, say the share as Z in the server. There are a few more things that need to be done because T appears in a few other places here, right? You are reading messages from T, as in you are receiving from T. T is declaring variables here. T is sending stuff. T is sending stuff. T is doing computation. For each of that, we have to say what the servers will do. And this is all very 3-line, 2-3-line code you would write in this case. If it's something more complicated like GMW or BGW, you might call sub-protocols instead of writing that in line here. And then later you can write, okay, so this was SUM, which had a trusted party. Here is a scheme. Here's my protocol, secure SUM. There's one line inside it says the secure SUM implements the functionality SUM, which is also a protocol, using the scheme linear MPC, where this T is that T, right? So T at T. And this underscore namespace is to say when you put in code, you have to put some prefix to not confuse things that are already, there may be variables here which are also used here. And you don't want to worry about keeping them separate. So you can specify some prefix that will be applied. Okay, so what this will result in when you compile as an intermediate step, you'll get MPC code, which will, which will have the secure summation. Okay, I'm kind of out of time, so let me very quickly tell you black box transformations. to support MPC in the head, you need a lot of features. You need to be able to manipulate a party. So you might need to open only some parties in a protocol, not all of them. You will need to tap into the ports they use to communicate with others. So there is a syntax for that. You need to set their random tape, read their random tape. You need to react to their communication when they try to send something out in a port or read from a port. So there is syntax for that. When they try to call a subroutine, a subprotocol, when they try to open a party, open a sub session, you want to react to that. So there's syntax for all of those. Basically, there are enough controls. We came up with this set of features because we're trying to make sure we can implement something like IPS, which is a pretty non-trivial protocol transformation. And there's all the things we needed to make sure we could conveniently do it. Yes, and we can do it. So Rajiv here was the main person implementing all of this. So this reference MPC compiler has over, it's a medium-sized project. This is all in C++ and Python. And it transforms MPC code into C++. It's very concurrent. Looking forward to all the multi-core systems that are becoming more common now. We use cores very freely. We have managed to implement a lot of the standard schemes. They are not very production ready. They're proof of concept implementations. But we have had student interns come in and do projects, take the latest crypto paper, something out there, and implement in our language, and they managed to do it, so it can be done. So we have written enough lines of MPC code now to say that our syntax is reasonably good. There's a lot of work to do. Documentation, for one. Very unoptimized backend currently. And there is a need to standardize file formats and so forth so that you can use, say you have pre-processed correlated keys that generated by some other tool, we would like to use it. Currently we don't do any of that. We just expect it to come in an arbitrary format we came up with. We do not do anything about handling side channels. I'm sure there are tons of timing channels here in our implementation. So, yeah, so there, this is not yet public, or rather this is the time it's going public. But if you go to that website, you won't see much other than this presentation and a little bit of announcement. But in the next few, as I said, weeks or months, we hope to have more things coming up there. It'll be open source. Contributions are welcome. Okay, thank you. Any quick comments, questions? Yeah.
Session types?
No, we don't use any session types. It's, currently deadlocks, there is nothing to prevent deadlocks. So it's up to the programmer.
So any future ideas or something?
We'd love to have, when we originally started this, there was a hope that we will do that eventually. We have not reached that point yet. Yeah.
Thank you for the interesting talk. How does the backend handle like synchrony versus asynchrony?
So right now, everything is essentially asynchrony. We have a way to time out. So you will have to, time out, or rather, you have to configure timeouts that we allow configuring timeouts. So you have to do that. Like it's asynchronous by default.
So it's like when you generate the configuration files, you fix the
timeout. Yeah, exactly.
Thank you.
What are the challenges that you faced regarding black box transformation protocols for
Yeah, black box.
especially into cyber security as such. And
Well, so black box transformations is something that's in the literature that has been successfully used to describe a lot of protocols. Our problem is when you try to support that in an implementation, there are all sorts of handles we need on this party. So there's a party running in your head as a black box, and it's trying to communicate with others, and you need to have syntax to tap into all those communications, modify them, make copies of parties with the same random tape and things like that. We need a lot of features. So supporting them is a challenge. Using them is also a little bit of a challenge because syntax is not as easy as you would like, as in they're somewhat complicated operations, so you end up with syntax which is a little non-intuitive, but we have tried to keep it as intuitive as possible. But once in a while we ourselves forget, because we don't have documentation to look up, we need to recall what the syntax meant. Yeah.
thank you.
Okay.
Hi, thanks for the great talk. Does the syntax support any parallelization of communication?
As in you can create big objects and send them.
Okay.
Right now no other support.
Okay.
So let us thank the speaker for an amazing talk. We will now pause for the lunch and we will resume at 2 p.m. You can take the doors towards your left for the lunch. Thanks.
Hello. Just a quick announcement. So from 4